Hello viewers of AraaTech. Today we are excited to present a brand new complete course on natural language processing. In this video, we will delve into its definition, its pivotal role in artificial intelligence, and its key components such as machine learning, neural networks, feature learning, fuzzy logic, transfer learning, robotics, speech recognition, and much more. Our aim is to make this complex topic accessible and understandable for both professionals and non-professionals alike. We will use a variety of easy-to-follow examples to illustrate concepts and ensure practical implementation is achievable. Don't forget to like, share, and subscribe to our channel for more insightful content. Let's start our topic. Natural language processing and artificial intelligence. Definition of NLP. Natural language processing. NLP is a field of computer science, artificial intelligence, and computational linguistics concerned with the interactions between computers and human natural languages. It focuses on the ability of computers to understand, interpret, and generate human language, including both spoken and written forms. Tokenization. Tokenization is the process of breaking down text into individual words or phrases, known as tokens. For example, the sentence, "I love natural language processing," would be tokenized into "I love natural language processing." This step is essential for many natural language processing tasks because it provides the basic units of analysis. Parsing. Parsing involves analyzing the grammatical structure of sentences to understand their meaning. For example, consider the sentence, "The cat sat on the mat." Parsing. This sentence involves identifying the subject, cat, the action, sat, and the object, mat. This understanding helps in tasks like language understanding and generation. Named entity recognition, NER. Named entity recognition involves identifying entities such as people, places, organizations, etc. within text. For example, in the sentence, "Steve Jobs was the CEO of Apple Incorporation," NER would identify Steve Jobs as a person and Apple Incorporation as an organization. Part of speech, POS, tagging. Part of speech tagging involves assigning grammatical tags, that is noun, verb, adjective, to words in a sentence. For example, in the sentence, "The quick brown fox jumps over the lazy dogs," POS tagging would assign tags like DT, determiner, to the JJ, adjective, to quick, NN, noun, to fox, etc. Semantic analysis. Semantic analysis involves understanding the meaning of text at a deeper level. This can include identifying relationships between words, disambiguation, word meanings, and capturing the underlying concepts conveyed by the text. Sentiment analysis. Sentiment analysis involves determining the sentiment, positive, negative, neutral, expressed in text. For example, in the sentence, "I loved the movie, it was fantastic," sentiment analysis would classify the sentiment as positive. Machine translation. Machine translation involves translating text from one language to another. For example, translating the English sentence, "Hello, how are you?" to French would result in "Bonjour," comment. Text generation. Text generation involves generating human-like text based on input or prompts. For example, given the prompt, "Once upon a time," a text generation model might generate a story beginning with those words. Question answering. Question answering involves answering questions based on a given context or knowledge base. For example, given a passage of text about World War II, a question answering system might be able to answer questions like when did World War II start or who were the Axis powers. These components collectively enable NLP systems to process, understand, and generate human language, powering a wide range of applications such as virtual assistants, language translation, and text analysis. Feature extraction. Natural language processing techniques are used to extract relevant features from the text data. These features capture various aspects of language such as word frequency, syntactic structure, semantic meaning, etc. These extracted features serve as input to artificial intelligence models for further processing. For example, in a text classification task, features might include the presence of certain keywords or phrases that are indicative of specific categories. Model training. Artificial intelligence models such as neural networks are trained using natural language processing tasks as objectives. The artificial intelligence model learns to perform these tasks by adjusting its internal parameters during training based on the patterns and relationships it discovers in the training data. For example, in language modeling, a model might be trained to predict the next word in a sentence given the previous words. In text classification, a model might be trained to classify text into different categories based on its content. Integration. Natural language processing components are integrated into artificial intelligence systems to enable human-like interaction, understanding, and generation of natural language. These components include various natural language processing models and algorithms for tasks such as speech recognition, language understanding, sentiment analysis, and more. For example, virtual assistants like Siri or Alexa use natural language processing to understand user queries and provide appropriate responses. Feedback loop. NLP-powered artificial intelligence systems can learn and improve over time based on feedback from users. This feedback allows the system to adapt to changing language patterns and user preferences, leading to more accurate and personalized interactions. For example, a chatbot might learn from user interactions to improve its ability to understand and respond to queries effectively. Overall, natural language processing plays a crucial role in enabling artificial intelligence systems to interact with and understand human language, leading to a wide range of applications such as virtual assistants, language translation, sentiment analysis, and more. Virtual assistants. Description. Virtual assistants such as Siri, Google Assistant, or Alexa use natural language processing to understand user queries and provide relevant responses. Example: user, what is the weather like today? Virtual assistant, the weather today is sunny with a high of 75 degrees. Sentiment analysis. Description. Natural language processing is used to analyze social media posts, customer reviews, and feedback to gauge sentiment and customer satisfaction. Example: review, I absolutely love this product. It exceeded my expectations. Sentiment analysis: positive. Language translation. Description. Natural language processing powers machine translation systems that translate text between different languages. Example: English, hello, how are you? Translation: Spanish, hola, ¿cómo estás? Information extraction. Description. Natural language processing techniques are used to extract structured information from unstructured text, such as extracting named entities or key phrases from documents. Example: text: Apple Incorporation was founded by Steve Jobs and Steve Wozniak in 1976. Named entity extraction, Apple Incorporation, Steve Jobs, Steve Wozniak, 1976. Text summarization. Description. Natural language processing is used to automatically summarize long text or documents into shorter, more digestible summaries. Example. Original text. A new study reveals breakthroughs in cancer research highlighting promising treatments and potential cures. Summarized text. Recent study shows promising breakthroughs in cancer research. Document classification. Description. Natural language processing techniques are employed to classify documents into different categories or topics automatically. Example. Document. Article discussing the latest advancements in artificial intelligence. Classification. Technology/artificial intelligence. Speech recognition. Description. NLP enables computers to transcribe and understand spoken language, powering applications like voice assistants and speech-to-text systems. Example. Spoken input. Set a timer for 10 minutes. Voice assistant. Timer set for 10 minutes. These applications demonstrate how natural language processing enhances artificial intelligence capabilities across various domains, making it possible for machines to understand, interpret, and generate human language for practical use. Ambiguity. Description. Natural language is rich with ambiguity, meaning that words or phrases can have multiple interpretations depending on the context. This ambiguity poses a significant challenge for computers to accurately understand the intended meaning of text. Example. The word bank can refer to a financial institution or the edge of a river. Without context, it's difficult for an NLP system to determine which meaning is intended in a given sentence, like I deposited money in the bank. Variability. Description. Language use varies greatly across different contexts, regions, and individuals. This variability makes it challenging to develop NLP models that can accurately generalize across diverse linguistic patterns. Example. The way people express the same idea can vary based on factors such as culture, age, education, and social background. For instance, the phrase, "How are you?" might be expressed as "What's up?" or "How is it going?" in informal contexts. Sarcasm and irony. Description. Understanding sarcasm, irony, humor, and other nuanced aspects of language remains a challenge for natural language processing systems. These forms of communication rely heavily on context and tone, which can be difficult for machines to interpret accurately. Example. In the sentence "Great job, Einstein," the word Einstein is used sarcastically to imply the opposite of its literal meaning. Without understanding the speaker's tone and context, an natural language processing system might interpret this as a compliment rather than sarcasm. Data quality and bias. Description. Natural language processing models are sensitive to biases present in training data, which can lead to unfair or inaccurate results. Biases can arise from various sources, including the way data is collected, annotated, or pre-processed, as well as societal biases embedded in language use. Example. In sentiment analysis, a model trained on biased datasets may inaccurately associate certain words or phrases with positive or negative sentiment, leading to biased predictions. Similarly, in language translation, biases present in training data can result in mistranslations or misinterpretations of culturally specific expressions. Addressing these challenges require ongoing research and innovation In the field of natural language processing, techniques such as context-aware modeling, domain adaptation, and bias mitigation strategies are being developed to improve the robustness and fairness of natural language processing systems. In summary, natural language processing is indeed a critical component of artificial intelligence that empowers computers to comprehend, interpret, and produce human language. This capability facilitates seamless and natural interaction between humans and machines, fostering a wide array of applications and domains, from virtual assistants and sentiment analysis to language translation and document classification. Natural language processing plays a pivotal role in bridging the gap between human communication and machine intelligence, ultimately enhancing user experiences and enabling innovative solutions across various industries. API model deployment. Natural language processing contributes significantly to various aspects of artificial intelligence, including API development, modeling, and deployment. Creation of natural language processing APIs. Natural language processing enables the development of APIs that provide easy access to a wide range of natural language processing functionalities. These APIs act as intermediaries, allowing developers to incorporate advanced language understanding capabilities into their applications without having to developing NLP algorithms or models from scratch. Developers can leverage existing natural language processing frameworks, libraries, and services to build APIs that offer functionalities such as text analysis, sentiment analysis, language translation, named entity recognition, part of speech tagging, and more. Natural language processing APIs abstract away the complexity of natural language processing algorithms and models, providing a simplified interface that developers can interact with to perform language processing tasks seamlessly. Streamlined interface for natural language processing capabilities. NLP APIs offer a streamlined interface for accessing a variety of language processing functionalities. Developers can interact with these APIs through well-defined endpoints, request parameters, and response formats, making it easy to integrate NLP capabilities into their applications. The APIs abstract away the intricacies of natural language processing algorithms and models, providing developers with high-level functions and methods that they can use to perform specific language processing tasks with minimal effort. Accepting text inputs and returning results. Natural language processing APIs are typically designed to accept text inputs such as sentences, paragraphs, or documents and return the results of natural language processing in a structured format. Developers can pass text data to the API endpoints and receive the processed results as output. The processed results may include information such as sentiment scores, language translations, named entities, part of speech tags, summaries, classifications, and more depending on the specific functionality provided by the API. Example APIs. Several popular examples of natural language processing APIs include Google Cloud Natural Language API, provides capabilities for sentiment analysis, entity recognition, syntax analysis, and content classification. Microsoft Azure Text Analytics API offers functionalities for sentiment analysis, key phrase extraction, language detection, and named entity recognition. IBM Watson Natural Language Understanding API provides features for sentiment analysis, entity extraction, concept tagging, emotion analysis, and more. In summary, natural language processing enables the development of APIs that streamline access to advanced language processing functionalities, allowing developers to easily integrate natural language processing capabilities into their applications without the need for extensive knowledge of natural language processing algorithms or models. These APIs offer a simplified interface for performing text analysis tasks, accepting text inputs, and returning processed results in a structured format, thereby facilitating the development of intelligent applications that can understand and interpret human language effectively. Development and training of artificial intelligence models. Natural language processing techniques serve as the foundation for developing and training artificial intelligence models that are capable of understanding and processing human language effectively. These models are built using various deep learning architectures, including recurrent neural networks (RNNs), convolutional neural networks (CNNs), and transformer models like BERT. Deep learning architectures provide the flexibility and scalability needed to handle the complexity of natural language, all allowing artificial intelligence models to learn intricate patterns, relationships, and representations of language from large volumes of text data. Training on large datasets. Natural language processing models are trained on large datasets of text data that are annotated with labels or structured information. These datasets contain examples of human language paired with corresponding annotations such as sentiment labels, named entities, part of speech tags, or semantic labels. Training on annotated datasets allows NLP models to learn from labeled examples, enabling them to recognize and understand patterns, relationships, and nuances in language. Learning patterns and representations of language. During the training process, natural language processing models learn to capture the underlying patterns and representations of language encoded in the text data. This involves learning to extract meaningful features, encode contextual information, and model semantic relationships between words and phrases. By learning from a diverse range of text data, natural language processing models acquire a deep understanding of language structure, semantic syntax, and context, enabling them to perform a wide range of language-related tasks with high accuracy and effectiveness. Fine-tuning for specific tasks or domains. Once trained on generic language data, natural language processing models can be fine-tuned for specific tasks or domains to improve their performance and adaptability. Fine-tuning involves retraining the pre-trained model on task-specific or domain-specific data to better align with the target task or domain. Fine-tuning allows natural language processing models to leverage the knowledge learned from generic language data and apply it to more specialized tasks, such as question answering, sentiment analysis, text classification, named entity recognition, language translation, and more. Example: BERT, bidirectional encoder representations from transformers. BERT is a pre-trained NLP model developed by Google that has been fine-tuned for various language-related tasks. BERT is based on transformer architecture and is capable of bidirectional language understanding, allowing it to capture context and dependencies from both directions of a sequence. BERT has achieved state-of-the-art performance on a wide range of NLP tasks, including question answering, sentiment analysis, text classification, named entity recognition, and more, demonstrating the effectiveness of deep learning models in modeling and understanding human language. In summary, natural language processing techniques are fundamental to the development and training of artificial intelligence models for language-related tasks. These models leverage deep learning architectures to learn patterns, relationships, and representations of language from large annotated datasets, allowing them to understand and process human language effectively. Natural language processing models like BERT demonstrate the power of deep learning in capturing the complexity of language and achieving state-of-the-art performance on various natural language processing tasks. Natural language processing model deployment. Natural language processing models can be deployed in various environments, including cloud platforms such as Amazon Web Services, AWS, Google Cloud Platform, GCP, Microsoft Azure, and IBM Cloud. Cloud platforms offer scalability, flexibility, and ease of management for deploying and hosting natural language processing models. Edge devices such as smartphones, tablets, IoT devices, and edge servers. Deploying natural language processing models on edge devices enables offline processing and real-time inference, reducing latency and bandwidth requirements. Web servers. Natural language processing models can be deployed on web servers to provide language processing capabilities for web applications and services. Optimization for efficiency and scalability. Deploying natural language processing models involves optimizing them for efficiency, scalability, and latency requirements to ensure optimal performance in production environments. Model optimization techniques include model quantization, model pruning, model distillation, and model compression to reduce model size and computational complexity. Deployment architectures such as microservices, serverless computing, and containerization can be used to improve scalability and resource utilization for natural language processing models. Integration with artificial intelligence applications. Natural language processing models are often deployed as part of larger artificial intelligence applications or services such as virtual assistant, chatbots, recommendation systems, and content analysis tools. Integration with artificial intelligence applications involves designing APIs for SDKs that expose natural language processing functionalities to developers and application users. Natural language processing models can be integrated with other artificial intelligence components such as speech recognition systems, knowledge graphs, and machine learning models to enhance the overall functionality and intelligence of artificial intelligence applications. Example, deployment on cloud platforms. Natural language processing models deployed on cloud platforms like AWS, GCP, and Azure enable developers to access powerful language processing capabilities through APIs or SDKs. Cloud-based deployment offers advantages such as scalability, reliability, security, and managed services for deploying, hosting, and managing natural language processing models. Developers can leverage cloud-based natural language processing services to quickly prototype, deploy, and scale artificial intelligence applications without the need for infrastructure management or upfront investment in hardware resources. Deployment of natural language processing models. Natural language processing models are optimized for efficiency, scalability, and latency requirements before deployment. They can be deployed on various environments including cloud platforms, edge devices, and web servers. Integration with artificial intelligence applications enhances their functionality, providing real-time language processing capabilities and boosting the intelligence of artificial intelligence systems. Role of natural language processing in the artificial intelligence ecosystem. Natural language processing is pivotal in API development, offering streamlined access to language processing functionalities. It serves as the foundation for modeling artificial intelligence systems, enabling them to understand, interpret, and generate human language effectively. Natural language processing's contributions span across API development, modeling and deployment, empowering the creation of intelligent applications that bridge the gap between humans and machines seamlessly. Python is indeed a popular choice for NLP due to its simplicity, readability, and vast ecosystem of libraries and tools tailored for natural language processing tasks. Install Python. First, you will need to install Python on your computer if you have not already. You can download the latest version of Python from the official website www.python.org. Follow the installation instructions for your operating systems. Choose an integrated development environment, IDE. An IDE can make your coding experience more efficient. Some popular choices for Python development include PyCharm, Visual Studio Code, and Jupyter Notebook. Choose one that suits your preferences and install it. Learn the basics. Start by learning the basics of Python programming language, including variables and data types, control flow, if statements, loops, functions and modules, lists, tuples and dictionaries, input-output operations. Explore Python libraries for natural language processing. Python has several powerful libraries specifically designed for natural language processing tasks. Some of the most commonly used ones include NLTK, Natural Language Toolkit, a comprehensive library for NLP tasks such as tokenization, stemming, tagging, parsing, and more. SPACY, another popular library for natural language processing that provides efficient tokenization, named entity recognition, dependency phrasing, and other functionalities. GenSim, a library for topic modeling, document similarity analysis, and other tasks related to natural language processing and understanding. Transformers, a library built by Hugging Face that provides pre-trained models for various natural language processing tasks, including BERT, GPT, and more. Practice with NLP projects. Once you are comfortable with the basics of Python, start working on natural language processing projects to apply your knowledge. You can find natural language processing projects, ideas online, or try replicating existing projects to gain hands-on experience. Join Python NLP communities. Engage with the Python and natural language processing communities to learn from others, ask questions, and share your knowledge. Participate in online forums, attend meetups or conferences, and contribute to open source projects to enhance your skills and network with like-minded individuals. Continuous learning. Python and natural language processing are vast fields, and there's always something new to learn. Stay updated with the latest developments, explore new libraries and techniques, and never stop experimenting and building projects to hone your skills. Tokenization. Tokenization is the process of breaking down a text into smaller units called tokens. These tokens can be words, phrases, or other meaningful elements of the text. The goal of tokenization is to divide the text into manageable units for further analysis or processing. In Python, you can tokenize text using libraries such as NLTK, Natural Language Toolkit, or SPACY. Here is a simple example using NLTK. Python copy code import NLTK from nltk.tokenize import word underscore tokenize. Text is equal to tokenization is an important step in natural language processing. Tokens is equal to word underscore tokenize text. Print tokens output CSS copy code. Tokenization is an important step in natural language processing. Stemming. Stemming is the process of reducing words to their root or base form. Known as the stem, it involves removing prefixes or suffixes from words to obtain the root form. Stemming is useful for reducing word variations and simplifying text for analysis or processing. In Python, you can perform stemming using libraries such as NLTK or Spacy. Here is an example using NLTK's Potter stemmer, Python copy code. From nltk.stem import Potter stemmer, stemmer is equal to Potter stemmer, word is equal to running, stem is equal to stemmer.stem word, print stem output. Arduino copy code run. Lemmatization. Lemmatization is similar to stemming but aims to reduce words to their base or dictionary form, known as the lemma. Unlike stemming, lemmatization ensures that the resulting word is a valid word in the language. Lemmatization takes into account the context of the word and applies morphological analysis to determine its lemma. In Python, you can perform lemmatization using libraries such as NLTK or Spacy. Here is an example using NLTK's WordNet Lemmatizer, Python copy code from nltk.stem import WordNet Lemmatizer. Lemmatizer is equal to WordNet Lemmatizer, word is equal to running, lemma is equal to lemmatizer.lemmatize word, print lemma, output Arduino copy code running. In summary, tokenization, stemming, and lemmatization are fundamental techniques in text processing for breaking down text into tokens, reducing word variations, and obtaining base forms of words respectively. These techniques are essential for various natural language processing tasks such as text classification, sentiment analysis, and information retrieval. NLTK, Natural Language Toolkit. NLTK is a comprehensive library for natural language processing tasks such as tokenization, stemming, lemmatization, part of speech tagging, parsing, and more. It provides a wide range of functionalities and tools for working with human language data. NLTK is widely used in academia and industry for research, education, and development of natural language processing applications. Example usage: Python copy code import NLTK from nltk.tokenize import word underscore tokenize nltk.download punkt. Text is equal to NLTK is a powerful library for natural language processing. Tokens is equal to word underscore tokenize text, print tokens. Spacy. Spacy is a modern and efficient library for natural language processing tasks designed for production use. It provides pre-trained models for tasks such as tokenization, part of speech tagging, named entity recognition, dependency parsing, and more. Spacy focuses on performance, scalability, and ease of use, making it suitable for building real-world NLP applications. Example usage: Python copy code import Spacy NLP is equal to spacy.load en underscore core underscore web underscore sm. Text is equal to Spacy is a fast and efficient library for NLP tasks. Doc is equal to NLP text. Tokens is equal to token.text for token in doc. Print tokens. Comparison. NLTK is more of a general purpose natural language processing library providing a wide range of functionalities and tools for natural language processing tasks. It's suitable for educational purposes, research, and prototyping. Spacy, on the other hand, is optimized for performance and efficiency, making it well suited for building production grade natural language processing applications. It provides pre-trained models and pipelines for various natural language processing tasks out of the box, while NLTK offers more flexibility and customization options. Spacy offers a more streamlined and efficient approach to natural language processing with its pre-trained models and optimized processing pipelines. Both NLTK and Spacy have their strengths and are widely used in the natural language processing community. The choice between them depends on the specific requirements of your project, your level of expertise, and your preferences regarding performance and ease of use. Syntax. Syntax refers to the rules governing the structure and arrangement of words to form meaningful sentences in a language. It deals with the order of words, phrases, and clauses in a sentence, as well as the relationships between them. Syntax encompasses various elements such as word order, sentence structure, grammatically role, subject, verb, object, syntactic, categories, noun, verbs, adjective, etc., and syntactic rules, that is subject, verb, agreement, tense, agreement. Syntax plays a crucial role in determining the grammatically and meaning of sentences in a language. Semantics. Semantics refers to the study of meaning in language, including how words, phrases, and sentences convey meaning and how meaning is interpreted by speakers and listeners. It deals with the relationship between linguistic expressions and the real-world entities, concepts, and events they refer to. Semantic encompasses various aspects such as lexical semantics, meaning of individual words, compositional semantics, meaning of phrases and sentences, and formal semantic, formal representation and analysis of meaning. Semantics addresses questions such as ambiguity, vagueness, reference, truth conditions, entailment, presupposition, and semantic relations, synonymy, antonymy, and hyponymy, etc. Morphology. Morphology refers to the study of the internal structure of words and the rules governing the formation of words in a language. It deals with morphemes, which are the smallest units of meaning or grammatical function in a language. Morphemes can be either free morphemes, standalone as words, or bound morphemes, prefixes, suffixes, infixes, etc. Morphology encompasses various processes such as inflection, modification of word forms to indicate grammatical features such as tense, number, gender, etc. Derivation, formation of new words by adding affixes, compounding, combination of two or more words to form a new word, and morphological alternations, changes in word forms to indicate grammatical or semantic distinctions. Morphology plays a fundamental role in word formation, word recognition, and word meaning in a language. Understanding syntax, semantics, and morphology is essential for analyzing and interpreting language at different levels of abstraction, from the structure of sentences to the meanings conveyed by words and phrases. These linguistic concepts provide the theoretical foundation for various fields of study, including linguistics, natural language processing, and computational linguistics. Regular expressions (REGEX) are powerful tools for manipulating and matching patterns in text. They allow you to search for specific patterns, extract information, and perform text transformations efficiently. Let's explore some common REGEX operations in Python. Matching patterns. You can use regular expressions to find patterns in text strings. For example, to check if a string contains a sequence of digits. Python copy code import RE. Text is equal to the price is $100, pattern is equal to R/D plus matches one or more digits if re.search pattern text print found a number in the text, else print no number found. Extracting information. You can use REGEX to extract specific information from text strings. For example, to extract all email addresses from a text, Python copy code text is equal to contact me at john@example.com or jane @example.com. Pattern is equal to r/b azazo9 percent plus minus @azazo9 minus plus /az2/b. Emails is equal to find all pattern text, print email addresses found. Substitution. REGEX can also be used to replace specific patterns in text strings. For example, to mask all phone numbers in a text with Python copy code text is equal to call me at 12345678890 or 98765432210. Pattern and all that formula. Splitting text. You can use REGEX to split text strings based on specific delimiters or patterns. For example, to split a string into a words, Python copy code text is equal to hello world. This is a sentence. Words is equal to RE split. RW plus text print words. Flags and options. REGEX supports various flags and options to modify matching behavior. For example, to perform a case insensitive search, Python copy code text is equal to the quick brown fox. Pattern is equal to rquick if re.search pattern text. Ignore case print found quick case insensitive. These are just a few examples of how you can use regular expressions in Python to manipulate and match patterns in text. Regular expressions offer a flexible and efficient way to perform complex text operations, but mastering them may require some practice and experimentation. Word embeddings are dense vector representations of words in a continuous vector space, where each word is represented by a fixed size vector. These embeddings capture semantic relationships between words, allowing for more effective and efficient processing of natural language. Let's explore three popular word embedding models: Word to VEC, GLOVE, Global Vector for Word Representation, and Fast Texts. Word to VEC. Word to VEC is a widely used word embedding model developed by Google. It learns word embeddings by predicting the context of word in a large corpus of text. Word to VEC consists of two main architectures: continuous bag of words CBOW and skipgram. CBOW predicts a target word based on its context words, while skipgram predicts context words given a target word. After training, word to VEC embeddings capture semantic relationships between words such as similarity and analogy. GLOVE. Global Vectors for Word Representation. GLOVE is a word embedding model developed by Stanford researchers. It learns word embeddings by factorizing the co-occurrence matrix of words in a corpus. GLOVE embeddings capture global word co-occurrence statistics, representing the likelihood of word pairs occurring together in context. GLOVE embeddings are trained using a global optimization objective, resulting in embeddings that capture both local and global semantic relationships between words. Fast text. Fast text is an extension of Word to VEC developed by Facebook Artificial Intelligence Research. It represents words as bags of character and grams and learns embeddings for subword units as well as whole words. Fast text embeddings capture morphological information and handle out of vocabulary words effectively by leveraging subword information. Fast text is particularly useful for language with rich morphology and for handling misspellings and rare words. These examples demonstrate how to use Word2Vec, Glove, and fast text models to obtain word embeddings in Python using the Gensim library. These pre-trained embeddings can then be used for various NLP tasks such as text classification, sentiment analysis, and machine translation. Additionally, you can train your own embeddings on custom corpora to tailor them to specific domains or tasks. Named Entity Recognition (NER) ChatGPT. Named Entity Recognition (NER) is a natural language processing task that involves identifying and classifying named entities in text into predefined categories such as person names, organization names, locations, dates, and more. NER is crucial for various NLP applications such as information extraction, question answering, and entity linking. Let's dive into NER and explore how to identify and classify entities in text using Python. Using Spacy. Spacy is a popular NLP library that provides pre-trained models for NER. Here is how you can perform NER using Spacy. Python copy code, import Spacy, hashtag load the English NER model. NLP is equal to spacy.load en underscore core underscore web underscore sm hashtag sample text. Text is equal to Apple is headquartered in Cupertino, California. Steve Jobs co-founded the company. Using custom models. For specific domains or languages, you may need to train custom NER models using annotated data. Libraries like Spacy and NLTK provide tools for training custom NER models on your own datasets. Named entity recognition is a fundamental task in natural language processing, enabling the extraction of structured information from unstructured text by identifying and classifying entities such as person names, organization names, locations, and more. NER facilitates various downstream NLP tasks and applications. Whether you are using pre-trained models or training custom models, NER is a powerful tool for extracting valuable insights from text data. Part of speech (POS) tagging is a fundamental task in natural language processing that involves labeling words in a text with their corresponding part of speech categories such as nouns, verbs, adjectives, adverbs, pronouns, etc. POS tagging is essential for various NLP tasks including syntactic analysis, text parsing, and information extraction. Let's explore how to perform POS tagging using Python. Using NLTK. NLTK Natural Language Toolkit provides a simple interface for performing POS tagging in Python. Here is how you can use NLTK for POS tagging. Python copy code import NLTK. From nltk.tokenize import word underscore tokenize slash hashtag sample text. Text is equal to NLTK is a powerful library for natural language processing. Hashtag tokenize the text. Tokens is equal to word underscore tokenize text. Hashtag perform POS tagging. Tagged underscore tokens is equal to nltk.pos underscore tag tokens. POS tagging provides valuable linguistic information about the syntactic structure and grammatical roles of words in a text. By labeling words with their corresponding part of speech categories, POS tagging facilitates various NLP tasks such as parsing, text generation, and information extraction. Whether you are using NLTK, Spacy, or other NLP libraries, POS tagging is a crucial step in the text processing pipeline for understanding and analyzing natural language text. Sentiment analysis is the process of computationally determining the sentiment, positive, negative, or neutral, expressed in a piece of text. It's a valuable tool in natural language processing for understanding opinions, attitudes, and emotions conveyed in textual data. Let's explore some techniques for performing sentiment analysis. Lexicon-based approach. Lexicon-based sentiment analysis relies on sentiment lexicons or dictionaries containing words annotated with their sentiment polarity, positive, negative, or neutral. The sentiment polarity of a text is determined by counting the number of positive and negative words and aggregating their scores. Machine learning approach. The machine learning approach to sentiment analysis involves training classification models on labeled datasets of text with sentiment labels. Features such as word frequencies, n-grams, and word embeddings are extracted from the text and used to train models such as logistic regression, support vector machines, or deep learning models. The trained models can then predict the sentiment of new text inputs based on their learned patterns. Here is an example of sentiment analysis using a logistic regression classifier with TF-IDF features in Python. Deep learning approach. Deep learning models such as recurrent neural networks RNNs, convolutional neural networks CNNs, and transformer models, that is BERT, have also been used for sentiment analysis. These models can learn complex patterns and relationships in the text data and often achieve state-of-the-art performance on sentiment analysis tasks. Pre-trained models such as BERT can be fine-tuned on sentiment analysis datasets to adapt them to specific domains or tasks. Here is an example of sentiment analysis using BERT with the Hugging Face Transformers library in Python. Naive Bayes. Naive Bayes classify our probabilistic models based on Bayes' theorem with the naive assumption of feature independence. They are computationally efficient and work well with high-dimensional data such as text. Naive Bayes classifiers are particularly effective for sentiment analysis, spam detection, and document categorization tasks. Support vector machines (SVM). SVMs are supervised learning model used for classification tasks, including text classification. They find the hyperlay that best separates the classes in the feature space. SVMs are powerful for handling high-dimensional feature spaces and can handle linear and non-linear classification tasks using different kernel functions. Deep learning neural networks. Deep learning models such as recurrent neural networks RNNs, convolutional neural networks CNNs, and transformer models, that is BERT, have revolutionized text classification. These models can learn complex patterns and relationship in text data and often achieve state-of-the-art performance on classification tasks. Pre-trained models such as BERT can be fine-tuned on classification dataset to adapt them to specific tasks and domains. Each of these algorithms has its advantages and is suitable for different types of text classification tasks. When choosing an algorithm, consider factors such as the size and complexity of your dataset, the interpretability of the model, and the computational resources available. Experimenting with different algorithms and techniques is often necessary to find the best approach for your specific problem. Learning scikit-learn and TensorFlow is a great way to master popular machine learning libraries for implementing natural language processing models. Here is a brief overview of each library and how they can be used for natural language processing. Scikit-learn. Scikit-learn is a powerful library for machine learning in Python. It provides simple and efficient tools for data mining and data analysis, including a wide range of supervised and unsupervised learning algorithms. For natural language processing, scikit-learn offers tools for text feature extraction, that is TF-IDF, vectorization, text classification, naive Bayes, SVM, and model evaluation. Example tasks you can perform with scikit-learn in NLP include sentiment analysis, document classification, and text clustering. TensorFlow. TensorFlow is an open source machine learning framework developed by Google. It provides a comprehensive ecosystem of tools, libraries, and community resources for building and deploying machine learning models. TensorFlow supports deep learning models including neural networks for various NLP tasks such as text classification, sequence labeling, machine translation, and language generation. TensorFlow's high-level API, Keras, offers a user-friendly interface for building and training deep learning models, making it accessible to beginners and experts alike. Example tasks you can perform with TensorFlow in natural language processing include sentiment analysis with recurrent neural networks, text classification with convolutional neural networks, and natural language understanding with transformer models like BERT. To master scikit-learn and TensorFlow for natural language processing, you can start by exploring their official documentation and tutorials, which provide comprehensive guides and examples for using the libraries. Additionally, there are many online courses, books, and resources available that cover both scikit-learn and TensorFlow in depth, allowing you to learn at your own pace and level of expertise. By gaining proficiency in scikit-learn and TensorFlow, you will be equipped with the necessary tools and knowledge to build and deploy advanced natural language processing models for a wide range of applications and use cases. Exploring deep learning for natural language processing involves understanding and working with advanced neural network architectures such as recurrent neural networks (RNNs) and transformer models. These architectures have revolutionized NLP by enabling models to capture complex patterns and long-range dependencies in sequential data like text. Let's dive into each of these models. Recurrent neural networks (RNNs). RNNs are a class of neural networks designed to work with sequential data, making them well suited for NLP tasks where input data has a sequential structure such as text. RNNs process input data one token at a time while maintaining an internal state, hidden state, that captures information from previous tokens. Long short-term memory (LSTM) and gated recurrent unit (GRU) are popular variants of RNNs designed to address the vanishing gradient problem and capture long-range dependencies more effectively. RNNs are commonly used for tasks like sentiment analysis, named entity recognition, machine translation, and text generation. Example libraries, frameworks for working with RNNs in NLP include TensorFlow, PyTorch, and Keras. Transformer models. Transformer models are a type of deep learning architecture that has gained popularity in recent years, particularly with the introduction of models like BERT, GPT, Generative Pre-trained Transformer, and its variants. Transformers rely on self-attention mechanisms to capture contextual relationships between words in a sequence, allowing them to model long-range dependencies more effectively compared to traditional RNNs. Transformer models consist of encoder and decoder layers, with each layer containing multi-head self-attention mechanisms and feed-forward neural networks. Pre-trained transformer models like BERT and GPT have achieved state-of-the-art performance on various NLP tasks, including question answering, sentiment analysis, text classification, and language generation. Example libraries, frameworks for working with transformer models in NLP include Hugging Face Transformers, TensorFlow, and PyTorch. To explore deep learning for NLP with RNNs and transformer models, you can start by studying the theoretical foundations of these architectures, understanding their components and how they operate on sequential data. Then, you can experiment with implementing RNNs and transformer models using popular deep learning frameworks like TensorFlow, PyTorch, or Hugging Face transformers. Additionally, working through tutorials, hands-on projects, and research papers in the field will help deepen your understanding and proficiency in using these advanced models for NLP tasks. Sequence-to-sequence models are a type of neural network architecture used for mapping input sequences to output sequences. They have become popular for various natural language processing NLP tasks, including machine translation, text summarization, and question answering. Let's explore sequence-to-sequence models and how they are used for tasks like translation and summarization. Architecture of sequence-to-sequence models. Sequence-to-sequence models consist of two main components, an encoder and decoder. The encoder processes the input sequence and produces a fixed size representation context vector that captures the input information. The decoder takes the context vector as input and generates the output sequence step by step, one token at a time. During training, the model is trained to minimize the difference between the generated output sequence and the target output sequence. Applications of sequence-to-sequence models. Machine translation. Sequence-to-sequence models have been successfully applied to machine translation tasks, where the input is a sequence of words in one language, source language, and the output is a sequence of words in another language, target language. Example models include the original sequence-to-sequence model with LSTM layers, as well as more advanced models like the transformer architecture, which has achieved state-of-the-art performance on machine translation benchmarks. Text summarization. Sequence-to-sequence models can also be used for text summarization tasks, where the input is a long document or article and the output is a concise summary capturing the main points of the input. Abstractive summarization models summarize by paraphrasing and rephrasing the input text, while extractive summarization models select and concatenate important sentences or phrases from the input. Transformer-based models like BART, bidirectional and auto-regressive transformers, have shown promising results for abstractive text summarization. Training and evaluation. Sequence-to-sequence models are trained using pairs of input and target sequences, with the model learning to generate the target sequences given the corresponding input sequences. Training involves optimizing the model parameters to minimize a loss function, typically a measure of the difference between the generated output sequences and the target output sequences. Models are evaluated on held out validation or test data using metrics such as BLEU, bilingual evaluation understudy, for machine translation, or rogue recall oriented understudy for gesting evaluation for text summarization. To understand the sequence-to-sequence models for tasks like translation and summarization, you can start by studying the foundational concepts of sequence-to-sequence learning and exploring tutorials and research papers on specific applications. Implementing sequence-to-sequence models using deep learning frameworks like TensorFlow or PyTorch and experimenting with different architectures and hyperparameters will deepen your understanding and proficiency in using these models for NLP tasks. Attention mechanisms play a crucial role in improving the performance of deep learning models for natural language processing, particularly in architectures like BERT bidirectional encoder representations for transformers and GPT generative pre-trained transformer. Let's explore the importance of attention mechanisms in these models. Importance of attention. Attention mechanisms allow models to focus on relevant parts of the input sequence while making predictions of generating output sequences. In natural language processing tasks, attention helps models capture long-range dependencies, understand context, and handle variable length sequences more effectively. By attending to different parts of the input sequence, models can assign varying levels of importance to each token, improving their ability to capture semantic relationships and syntactic structures in the data. BERT bidirectional encoder representations from transformers. BERT is a pre-trained transformer-based model developed by Google that has achieved state-of-the-art results on various NLP benchmarks. BERT uses a multi-layer directional transformer encoder architecture which incorporates attention mechanisms at each layer. The self-attention mechanism in BERT allows the model to attend to all positions in the input sequence simultaneously, capturing both left and right context. BERT's attention mechanism enables it to generate contextualized word embeddings that capture the meaning of words based on their surrounding context, leading to better performance on downstream natural language processing tasks such as sentiment analysis, named entity recognition, and question answering. GPT, Generative Pre-trained Transformer. GPT is another transformer-based model developed by OpenAI that has achieved impressive results in NLP tasks. GPT uses a decoder-only transformer architecture where attention mechanisms are applied to capture dependencies between tokens in the input sequence while generating output tokens autoregressively. GPT's attention mechanism allows it to generate coherent and contextually relevant text by attending to relevant parts of the input sequence during the generation process. By attending to different parts of the input sequence, GPT can generate high quality text that maintains coherence and relevance, making it suitable for tasks like text generation, conversation, modeling, and language understanding. In summary, attention mechanisms are essential components of advanced NLP models like BERT and GPT, allowing them to capture long-range dependencies and contextual information input sequences more effectively. By attending to relevant parts of the input sequence, these models can generate better representations of text data and achieve state-of-the-art performance on various natural language processing tasks. Transfer learning in natural language processing involves leveraging pre-trained language models and fine-tuning them on domain-specific or task-specific datasets to improve performance on downstream natural language processing tasks. Let's explore the concept of transfer learning in NLP and how fine-tuning pre-trained models works. Pre-trained language models. Pre-trained language models are large neural network architectures trained on vast amounts of text data using unsupervised learning objectives, such as language modeling or masked language modeling. These models learn rich representations of language by capturing semantic relationships, syntactic structures, and contextual information from the input text. Examples of pre-trained language models include BERT, GPT, XLNet, Roberta, and T5, among others. Fine-tuning pre-trained models. Fine-tuning pre-trained models involves updating the parameters of the pre-trained model using a smaller task-specific dataset. The process typically involves loading a pre-trained model that has been trained on a large corpus of text data, adding task-specific layers of modifying the existing architecture to adapt the model to the downstream task, fine-tuning the model on the task-specific dataset by updating the model parameters using backpropagation and gradient descent. Fine-tuning allows the model to learn task-specific patterns and relationships from the limited labeled data available for the downstream task while retaining the knowledge and representations learned during pre-training. Benefits of transfer learning in natural language processing. Transfer learning in natural language processing offers several advantages. Efficient use of resources. Pre-trained models capture general linguistic knowledge from large text corpora, reducing the need for extensive labeled data and computational resources during fine-tuning. Improved performance. Fine-tuning pre-trained models on task-specific datasets often leads to better performance compared to training models from scratch, especially for tasks with limited labeled data. Common transfer learning scenarios in natural language processing. Transfer learning is commonly used in various NLP tasks, including text classification, fine-tuning pre-trained models like BERT for sentiment analysis, topic classification or document categorization, named entity recognition, NER, adapting pre-trained models like BERT or Roberta for identifying entities such as people, organizations, and locations in text. See machine translation. Fine-tuning pre-trained models like T5 or MT for translation tasks between different languages, text generation. Fine-tuning models like GPT for generating coherent and contextually relevant text in specific domains or styles. Pre-trained GPT models. Start by selecting a pre-trained GPT model from libraries like Hugging Face Transformers or OpenAI's GPT-3. These models are already trained on massive amounts of text data and can generate coherent and contextually relevant text across various domains and styles. Fine-tuning GPT for text generation. Fine-tuning GPT involves adapting the pre-trained model to a specific task or dataset by updating its parameters with task-specific data. Prepare a dataset of text samples relevant to your task or domain. For example, if you are fine-tuning GPT for generating poetry, you would use a dataset of poems. Fine-tune the pre-trained GPT model on your dataset by providing the text samples as input and training the model to generate coherent and relevant text based on the input samples. Fine-tuning typically involves updating the model's parameters using techniques like gradient descent and backpropagation, similar to training a neural network. Text generation with fine-tuned GPT. Once the GPT model is fine-tuned on your dataset, you can use it to generate text samples relevant to your task or domain. Provide a prompt or seed text to the fine-tuned GPT model and let it generate text based on the provided input. Experiment with different prompts, sampling techniques, and temperature settings to control the creativity and diversity of the generated text. Evaluate the quality and coherence of the generated text samples to assess the performance of the fine-tuned GPT model. Examples of text generation tasks. The generation with GPT can be applied to various tasks and domains, including A. Creative writing, generating stories, poems, or dialogues. B. Content creation, generating articles, blog posts, or product descriptions. C. Chatbots, generating responses in conversational agents or virtual assistants. D. Code generation, generating code, snippets, or programmatic text. E. Translation, generating translations of text between different languages. Experimentation and iteration, experiment with different hyperparameters, architectures, and training strategies to fine-tune GPT for optimal performance on your text generation task. Iterate on the fine-tuning process by evaluating the generated text samples, identifying areas for improvement, and adjusting the model accordingly. By experimenting with large-scale language models like GPT for text generation, you can leverage the power of pre-trained models to generate high-quality and contextually relevant text across a wide range of tasks and domains. Co-reference resolution is a natural language processing task that involves identifying when words or phrases in a text refer to the same entity. It's essential for understanding the relationships between entities mentioned in a document or conversation. Definition: co-reference occurs when two or more expressions in a text refer to the same entity. For example, in the sentence, John went to the store, he bought some groceries, he refers to John. Co-reference resolution aims to detect, add links these referencing expressions mentions to their corresponding entities, antecedents in the text. Challenges: co-reference resolutions is challenging due to various linguistic phenomena, including pronouns, definite and indefinite noun phrases, demonstratives, and named entities. Resolving co-reference requires understanding the context, syntactics, structure, and semantics of the text to identify potential antecedents for each mention accurately. Approaches: rule-based approaches. These approaches rely on handcrafted rules and patterns to identify co-reference relations based on linguistic features such as agreement, proximity, and syntactic structure. While effective in some cases, rule-based system may struggle with ambiguity and complex linguistic constructions. Machine learning approaches. Machine learning models, particularly neural network-based models, have shown promising results in co-reference resolution. These models learn to identify co-reference relations from annotated training data, capturing both local and global contextual information. End-to-end models. End-to-end co-reference resolution systems directly predict co-reference links between mentions in a text without intermediate steps. These models often use neural network architectures like mention pair scoring or cluster ranking models. Evaluation. Co-reference resolution systems are evaluated based on metrics such as precision, recall, and F1 score, which measure the system's ability to correctly identify co-reference links between mentions. Evaluation datasets such as the CONLL 2012 shared task dataset provide annotated corpora for training and evaluating co-reference resolution systems. Applications. Co-reference resolution is crucial for various NLP applications, including information extraction, question answering, summarization, and dialogue systems. By resolving co-reference, natural language processing systems can produce more coherent and accurate representations of textual data, improving their performance across multiple tasks. Tools and libraries. Several natural language processing libraries and tools provide co-reference resolution capabilities, including Stanford Core NLP, Spacy, Allen NLP, and Hugging Face transformers. These tools offer pre-trained models and APIs for performing co-reference resolution tasks. By understanding co-reference resolution, natural language processing systems can better comprehend the nuances of language and accurately interpret text, leading to more effective and sophisticated natural language understanding capabilities. Chatbots. Definition. Chatbots are computer programs designed to simulate human conversation, typically through text or voice interfaces. They use natural language processing techniques to understand user input, generate responses, and engage in dialogue. Functionality. Chatbots can perform various tasks, including answering questions, providing recommendations, assisting with customer support, scheduling appointments, and conducting transactions. Natural language processing techniques. Chatbots leverage natural language processing techniques such as natural language understanding (NLU) to parse user queries, entity recognition to identify relevant information, sentiment analysis to understand user sentiment, and natural language generation (NLG) to generate human-like responses. Examples. Popular chatbots include virtual assistants like Siri, Google Assistant, and Amazon Alexa. Customer service chatbots on websites and messaging platforms, and conversational agents in social media apps. Question answering systems. Definition. Question answering systems are artificial intelligence systems designed to provide answers to user questions posed in natural language. Functionality. Question answer systems can answer questions across various domains and topics, ranging from factual inquiries to complex reasoning tasks. NLP techniques. Question answer systems use NLP techniques such as information retrieval to retrieve relevant documents or passages, text processing to understand the structure and semantics of questions, and machine learning models to match questions with appropriate answers. Types of question answer systems. Factoid question answer, answering questions with specific factual answers such as who is the President of the United States. List question answer, providing a list of entities or items that match the query, such as list of capital cities in Europe. Descriptive question answer, generating descriptive answers to open-ended questions such as why is the sky blue? Examples. Question answer systems include search engines like Google Search, which provides direct answers to queries in addition to search results, as well as domain-specific question answer systems for tasks like medical diagnosis, legal research, and customer support. Machine learning. Sure, let's break down the integration of natural language processing with machine learning and cover how to create APIs, the role of NLP in ML, as well as challenges, pros and cons. Integration of NLP with machine learning. Role of NLP in machine learning. Natural language processing techniques are used in machine learning tasks to process and understand human language data, enabling machines to analyze, interpret, and generate text-based information. How natural language processing helps in machine learning. Natural language processing provides tools and techniques for processing unstructured text data, such as tokenization, part of speech tagging, named entity recognition, sentiment analysis, and text classification. By incorporating natural language processing features and representations, machine learning models can learn to extract meaningful information from text data and make predictions or decisions based on language patterns. Natural language processing also enables machine learning models to interact with users through natural language interfaces such as chatbots, virtual assistants, and question answering systems, enhancing user experience and accessibility. Creating APIs for natural language processing with machine learning. Definition. An API, application programming interface, for natural language processing with machine learning allows developers to access natural language processing functionalities and machine learning models through a standardized interface. Steps to create an natural language processing API. Choose an NLP library or framework, that is NLTK, C, TensorFlow, PyTorch, and machine learning model architecture suitable for your task or application. Develop and train your natural language processing based machine learning models using labeled data or pre-trained models. Wrap your trained model with an API framework, that is Flask, Fast API, to expose it as a web service. Define endpoints for different natural language processing functionalities, that is text classification, sentiment analysis, and implement request handling logic to process incoming text data. Deploy your API to a web server or cloud platform to make it accessible over the internet. Role of NLP in creating APIs. Natural language processing plays a central role in creating APIs for text processing tasks by providing the underlying techniques and algorithms needed to understand and analyze natural language data. Natural language processing APIs abstract away the complexities of implementing natural language processing models, allowing developers to integrate sophisticated language processing capabilities into their applications with minimal effort. Challenges: data quality and bias. NLP models are sensitive to biases and errors present in training data, leading to biased or inaccurate results, especially in areas like sentiment analysis and named entity recognition. Domain adaptation. Natural language processing models trained on generic datasets may not perform well on domain-specific tasks or languages, requiring adaptation or fine-tuning on target domains or languages. Ambiguity and context understanding. Natural language is inherently ambiguous, making it challenging for natural language processing models to understand context and resolve ambiguities accurately. Pros and cons. Pros. Natural language processing enables machine to understand and interact with human language, opening up opportunities for applications in customer services, information retrieval, sentiment analysis, and more. Natural language processing APIs simplify the integration of language processing capabilities into applications, allowing developers to leverage pre-trained models and off-the-shelf tools. Cons. Building accurate and robust natural language processing models requires large amounts of annotated data and computational resources. Natural language processing models may struggle with handling complex linguistic phenomena, cultural nuances, and domain-specific jargon, leading to errors and misunderstanding in language processing tasks. Overall, the integration of NLP with ML through APIs offers powerful capabilities for processing and understanding human language, but it also presents challenges related to data quality, domain adaptation, and linguistic ambiguity that need to be addressed for effective application development. Modeling. Selecting a model architecture. Choose an appropriate model architecture based on the specific natural language processing task you want to solve. Common architecture include recurrent neural networks (RNNs), convolutional neural networks (CNNs), transformer models, that is BERT, GPT, and their variants. Pre-processing and feature engineering. Pre-process the text data by tokenizing, normalizing, and encoding it into a format suitable for the chosen model architecture. Perform feature engineering if necessary, such as extracting linguistic features or embeddings. Training the model. Train the selected model on labeled or annotated text data using supervised learning techniques. Optimize the model parameters using optimization algorithms like stochastic gradient descent (SGD) or ADAM, and monitor performance metrics on validation data to prevent overfitting. Fine-tuning optional. Fine-tune pre-trained models, that is BERT, GPT, on domain-specific or task-specific data to adapt them to your specific requirements and improve performance on downstream tasks. Evaluation. Evaluate the trained model on held out test data using appropriate evaluation metrics for the specific natural language processing task such as accuracy, precision, recall, F1 score, or perplexity. Deployment. Creating an API. Wrap the training natural language processing model with an API framework, that is Flask, Fast API. To expose it as a web service, define endpoints for different NLP functionalities, that is text classification, sentiment analysis, and implement request handling logic to process incoming text data. Containerization. Optional. Containerize your API using containerization platforms like Docker to ensure consistency and portability across different environments. Deploying to a cloud platform. Deploy your containerized API to a cloud platform like Amazon Web Services AWS, Google Cloud Platform GCP, or Microsoft Azure. Used platform specific services like AWS, LAMBDA, Google Cloud Functions, or Azure Functions for sphereless deployment, or deploy to virtual machines, VMS, or Kubernetes clusters for more control and scalability. Monitoring and scaling. Monitor the deployed API for performance, reliability, and resource utilization. Implement scaling strategies to handle fluctuations in traffic and ensure optimal performance under varying loads. Security and compliance. Implement security measures such as authentication, authorization, encryption, and compliance with data privacy regulations, that is GDPR, to protect sensitive data and ensure regulatory compliance. Continuous integration, continuous deployment, CI/CD. Set up CI/CD pipelines to automate the process of building, testing, and deploying updates to your natural language processing model and API, ensuring rapid iteration and deployment cycles. By following these steps for modeling and deployment, you can develop and deploy NLP models effectively, enabling them to process and analyze text data, extract insights, and provide valuable functionality in various applications and domains. Neural network. Integrating natural language processing with neural networks is a powerful approach that enables machines to understand and generate human language. Here is a comprehensive guide from beginners to professional on how natural language processing syncs with neural networks, including creating APIs, the role of NLP, challenges and pros and cons. Role of NLP in neural networks. Understanding text data. Natural language processing techniques help neural networks understand and process text data, which is essential for a wide range of applications such as sentiment analysis, text classification, machine translation, and question answering. Feature extraction. Natural language processing provides methods for extracting meaningful features from text, such as word embeddings, which represent words as dense vectors in a high-dimensional space. These embeddings capture semantic relationships between words, allowing neural networks to learn from text data more effectively. Generating text. Natural language processing techniques enable neural networks to generate human-like text by modeling language patterns and structures. This is particularly useful for tasks like text generation, dialogue systems, and language translation. Creating APIs for natural language processing with neural networks. Choose a framework. Select a deep learning framework like TensorFlow or PyTorch, which provides tools and libraries for building neural networks and integrating natural language processing functionalities. Model development. Develop your neural network model using the chosen framework, incorporating natural language processing techniques as needed for your specific task. This may involve designing the architecture of the neural network, pre-processing text data, and training the model on labeled datasets. API implementation. Wrap your trained neural network model with an API using a web framework like Flask or Django. Define endpoints that accept text input and return the model's predictions or outputs. Deployment. Deploy your API to a web server or cloud platform, making it accessible over the internet. Consider using containerization tools like Docker for packaging your API and ensuring consistency across different environments. Role of NLP in API creation. Data pre-processing. Natural language processing techniques are used to pre-process text data before it is fed into the neural network model. This may involve tokenization, normalization, and encoding of text data to prepare it for processing. Model integration. Natural language processing provides methods for integrating the neural network model with the API, allowing users to interact with the model through text inputs and receive predictions or outputs in response. Error handling. Natural language processing techniques can be used to handle errors and edge cases in text input, ensuring robustness and reliability of the API. Challenges. Data quality. Natural language processing models require large amounts of high quality labeled data for training, which may be difficult to obtain, especially for specialized domains or languages. Computational resources. Training and deploying neural network models for natural language processing tasks can be computationally intensive and require significant computational resources, including GPU, accelerators, and memory. Pros and cons. Pros. Natural language processing with neural networks enables machines to understand and generate human language, opening up possibilities for a wide range of applications in natural language understanding and generation. APIs for natural language processing with neural networks provide a convenient and accessible way for developers to integrate language processing capabilities into their applications. Cons. Developing and deploying neural network models for natural language processing tasks can be complex and resource intensive, requiring expertise in deep learning and computational resources. Natural language processing models may struggle with handling ambiguity, context understanding, and culture nuances in language, leading to errors and inaccuracies in text processing tasks. By understanding the role of natural language processing in neural networks, creating APIs for natural language processing tasks, and considering the associated challenges, pros and cons, students can gain valuable insights into the integration of natural language processing with deep learning for natural language understanding and generation. Modeling and deployment are essential steps in the development and implementation of natural language processing systems. Modeling. Selecting model architecture. Choose an appropriate model architecture based on the natural language processing task at hand. Common architectures include recurrent neural networks (RNNs), convolutional neural networks (CNNs), transformer-based models that is BERT, GPT, and their variations. Data pre-processing. Pre-process the text data by tokenizing, cleaning, and normalizing it. Convert the text into numerical representations, that is word embeddings, suitable for input into the chosen model architecture. Model training. Train the selected model on a labeled dataset using supervised learning techniques. Use optimization algorithms like stochastic gradient descent (SGD) or ADAM to update the model parameters and minimize the loss function. Hyperparameter tuning. Fine-tune the model hyperparameters, that is learning rate, batch size, number of layers, to optimize performance on the validation dataset. Experiment with different configurations to achieve the best results. Validation and evaluation. Evaluate the trained model on a separate validation dataset to assess its performance matrix, that is accuracy, precision, recall, F1 score. Iterate on the model architecture and hyperparameters based on validation results. Deployment. API development. Wrap the trained model with an API application programming interface to expose its functionality over the web. Use frameworks like Flask or Django to create RESTful APIs that accept text input and return model predictions. Containerization. Containerize the API using Docker to encapsulate the model, its dependencies, and the API code into a portable container. This ensures consistency and reproducibility across different environments. Deployment to cloud platform. Deploy the containerized API to a cloud platform such as Amazon Web Services, Google Cloud Platform (GCP), or Microsoft Azure. Use platform-specific services like AWS, Elastic Beanstalk, Google Kubernetes Engine (JKE), or Azure App Service for container deployment. Security. Secure the API endpoints with authentication mechanisms such as API keys, OAuth tokens, or JWT. Implement encryption to protect data transmitted over the network. Continuous integration, continuous deployment. Set up CI/CD pipelines to automate the process of building, testing, and deploying updates to the API. Use tools like Jenkins, Circle CI, or GitLab CI/CD for automated deployment and version control. By following these steps for modeling and deployment, you can develop robust NLP systems and make them accessible to users through APIs deployed on scalable and reliable infrastructure. How natural language processing helps in deep learning. Natural language processing provides techniques for text pre-processing, feature extraction, semantic representation, and language modeling, which are essential for building deep learning models for NLP tasks. Deep learning models such as recurrent neural networks (RNNs), convolutional neural networks (CNNs), and transformer-based architectures, that is BERT GPT, leverage NLP representations and embeddings to learn complex patterns and relationships in text data, creating APIs for NLP with deep learning. Choose a deep learning framework. Select a deep learning framework like TensorFlow, PyTorch, or Keras, which provides tools and libraries for building neural networks and implementing NLP functionalities. Model development. Develop your deep learning model using the chosen framework, incorporating NLP techniques and features as needed for your specific task. This may involve designing the architecture of the neural network reprocessing text data and training the model on labeled datasets. API implementation. Wrap your trained deep learning model with an API using a web framework like Flask or Django. Define endpoints that accept text input and return the model's predictions or outputs. Deployment. Deploy your API to a web server or cloud platform, making it accessible over the internet. Consider using containerization tools like Docker for packaging your API and ensuring consistency across different environments. Role of NLP in API creation. Data pre-processing. NLP techniques are used to pre-process text data before it is fed into the deep learning model. This may involve tokenization, normalization, and encoding of text data to prepare it for processing. Model integration. NLP provides methods for integrating the deep learning model with the API, allowing users to interact with the model through text inputs and receive predictions or outputs in response. Error handling. NLP techniques can be used to handle errors and edge cases in text input, ensuring robustness and reliability of the API. Challenges. Data quality. Deep learning models for NLP tasks require large amounts of high quality labeled data for training, which may be difficult to obtain, especially for specialized domains or languages. Computational resources. Training and deploying deep learning models can be computationally intensive and require significant computational resources, including GPU, accelerators, and memory. Model interpretability. Deep learning models are often considered black box models, making it challenging to interpret their predictions and understand how they arrive at decisions, which can be a concern for applications requiring transparency and accountability. Pros and cons. Pros. NLP with deep learning enables machines to understand and generate human language, opening up possibilities for a wide range of applications in natural language understanding and generation. APIs for NLP with deep learning provide a convenient and accessible way for developers to integrate language processing capabilities into their applications. Cons. Developing and deploying deep learning models for NLP tasks can be complex and resource intensive, requiring expertise in deep learning and computational resources. NLP models may struggle with handling ambiguity, context understanding, and cultural nuances in language, leading to errors and inaccuracies in text processing tasks. By understanding the role of NLP in deep learning, creating APIs for NLP tasks, and considering the associated challenges, pros, and cons, students can gain valuable insights into the integration of NLP with deep learning for natural language understanding and generation. Modeling and deployment are crucial steps in the development and implementation of natural language processing systems. Modeling. Choose model architecture. Select an appropriate model architecture based on the specific NLP task you want to solve. Common architectures include recurrent neural networks (RNNs), convolutional neural networks (CNNs), transformer model like BERT and their variations. Data preprocessing. Pre-process the text data by cleaning, tokenizing, and encoding it into a format suitable for input into the chosen model architecture. This may involve techniques like word embedding, padding sequences, and handling out of vocabulary words. Model training. Train the selected model on labeled data using supervised learning techniques. Optimize the model parameters using optimization algorithms such as stochastic gradient descent, or ADAM. Monitor the model's performance on a validation dataset and adjust hyperparameters as necessary to prevent overfitting. Evaluation. Evaluate the trained model's performance on a separate test dataset using appropriate evaluation metrics for the specific NLP task, such as accuracy, precision, recall, F1 score, or perplexity. Iterate on the model architecture and hyperparameters based on evaluation results to improve performance. Deployment. Create API. Wrap the trained model with an API, application programming interface, to expose its functionality over the web. Use frameworks like Flask or Django to create RESTful APIs that accept text input and return model predictions. Containerization. Containerize the API using Docker to encapsulate the model, its dependencies, and the API code into a portable container. This ensures consistency and reproducibility across different environments. Deployment to cloud. Deploy the containerized API to a cloud platform such as Amazon Web Services, AWS, Google Cloud Platform, GCP, or Microsoft Azure. Use platform-specific services like AWS, Elastic Beanstalk, Google Kubernetes Engine (GKE), or Azure App Service for container deployment. Fuzzy logic. Integrating natural language processing (NLP) with fuzzy logic offers a flexible and nuanced approach to understanding and processing human language. Here is a comprehensive guide from beginners to professional on how NLP syncs with fuzzy logic, including creating APIs, the role of NLP, challenges, and pros and cons. NLP sync with fuzzy logic. Role of NLP in fuzzy logic. NLP techniques provide the ability to handle the inherent ambiguity and uncertainty present in human language. Fuzzy logic complements NLP by offering a framework to represent and reason with uncertain and imprecise information. How NLP helps in fuzzy logic. NLP techniques enable the extraction of linguistic features and context from text data, which can be used as inputs to fuzzy logic systems. Fuzzy logic provides mechanisms to model linguistic variables, fuzzy sets, and fuzzy rules, allowing for the representation of imprecise linguistic concepts in NLP tasks. Creating APIs for NLP with fuzzy logic. Choose a fuzzy logic framework. Select a fuzzy logic framework or library such as scikit-fuzzy or pyfuzzy that provides tools for fuzzy set operations, fuzzy inference, and rule-based reasoning. Model development. Develop a fuzzy logic system that incorporates linguistic variables and fuzzy rules based on the linguistic features extracted from the text data using NLP techniques. API implementation. Wrap the fuzzy logic system with an API using a web framework like Flask or Django. Define endpoints that accept text input and return the fuzzy logic system's outputs or predictions. Deployment. Deploy the API to a web server or cloud platform, making it accessible over the internet. Use containerization tools like Docker for packaging the API and ensuring consistency across different environments. Role of NLP in API creation. Text pre-processing. NLP techniques are used to pre-process text data before input into the fuzzy logic system. This may involve tasks such as tokenization, stemming, and removing stop words to extract linguistic features. Feature extraction. NLP provides methods for extracting linguistic features and context from text data, which can be used as inputs to the fuzzy logic system. Error handling. NLP techniques can be used to handle errors and edge cases in text input, ensuring robustness and reliability of the API. Challenges. Interpretability. Fuzzy logic system can be complex and difficult to interpret, especially when combined with the inherently complex nature of human language processed by NLP techniques. Scalability. Implementing fuzzy logic systems for large-scale NLP tasks may pose challenges in terms of computational complexity and resource requirements. Integration complexity. Integrating NLP with fuzzy logic requires expertise in both domains and careful design to ensure compatibility and effectiveness. Pros and cons. Pros. Combining NLP with fuzzy logic offers a flexible and intuitive approach to handling uncertainty and imprecision in natural language understanding and processing. APIs for NLP with fuzzy logic provide a user-friendly interface for developers to integrate linguistic reasoning capabilities into their applications. Cons. Developing and deploying fuzzy logic systems for NLP tasks can be challenging and require expertise in both NLP and fuzzy logic. Fuzzy logic systems may struggle with scalability and efficiency issues, especially in large-scale or real-time NLP applications. By understanding the role of NLP in fuzzy logic, creating APIs for NLP tasks with fuzzy logic, and considering the associated challenges, pros and cons, students can gain valuable insights into the integration of linguistic reasoning with natural language understanding and processing. Modeling and deployment are essential steps in building and implementing natural language processing systems with fuzzy logic. Modeling. Define linguistic variables. Identify the linguistic variables relevant to your NLP task, such as sentiment, relevance, or intensity. These variables represent fuzzy concepts and are defined by their membership functions. Fuzzy membership functions design membership functions to quantify the degree to which linguistic variables belong to each fuzzy set. Membership functions capture the uncertainty and imprecision inherent in natural language data. Fuzzy rules define fuzzy rules that relate the input linguistic variables to the output linguistic variables. These rules encode expert knowledge for domain-specific heuristics for reasoning about the input text data. Inference engine implement an inference engine that applies fuzzy logic reasoning to the input linguistic variables based on the defined fuzzy rules. The inference engine combines the input information to generate crisp outputs or conclusions. Model training and optimization fine-tune the fuzzy logic model parameters, including membership functions and fuzzy rules, using training data. Optimization techniques such as genetic algorithms or gradient descent can be used to improve model performance. Create API. Wrap the trained fuzzy logic model with an API application programming interface to expose its functionality over the web. Use frameworks like Flask or Django to create RESTful APIs that accept text input and return fuzzy logic based predictions or outputs. Containerization. Containerize the API using Docker to package the fuzzy logic model, its dependencies, and the API code into a portable container. This ensures consistency and reproducibility across different deployment environments. Deployment to cloud. Deploy the containerized API to a cloud platform such as Amazon Web Services, AWS, Google Cloud Platform, GCP, or Microsoft Azure. Utilize platform-specific services like AWS, Elastic Beanstalk, Google Kubernetes Engine, GKE, or Azure App Service for container deployment. Scaling and monitoring. Monitor the deployed API for performance metrics such as response time, throughput, and error rates. Implement scaling strategies to dynamically adjust resource allocation based on incoming traffic to ensure scalability and reliability. Security. Secure the API endpoints with authentication mechanisms such as API keys or OAuth tokens. Implement encryption, that is HTTPS, to protect data transmitted over the network. Regularly update and patch software components to mitigate security vulnerabilities by following these steps for modeling and deployment. You can develop and deploy NLP systems with fuzzy logic, providing robust and interpretable solutions for processing natural language data. Reinforcement learning. Integrating natural language processing with reinforcement learning offers exciting possibilities for training artificial intelligence models to interact with and understand human language. Natural language processing sync with reinforcement learning. Role of natural language processing in reinforcement learning. NLP provides the means for machines to understand and process human language, enabling reinforcement learning agents to interact with users through natural language interfaces. How natural language processing helps in reinforcement learning. Natural language processing techniques enable reinforcement learning agents to understand user queries, feedback, and instructions expressed in natural language, allowing for more intuitive and human-like interaction. Reinforcement learning algorithms can leverage natural language processing representations of text data to learn policies and make decisions in language-rich environments such as dialogue systems, text-based games, and virtual assistants. Creating APIs for natural language processing with reinforcement learning. Choose reinforcement learning framework. Select an reinforcement learning framework such as OpenAI GIM, Stable Baseline, or DeepMind's Dopamine that supports integration with natural language processing components. Model development. Develop an reinforcement learning agent that interacts with a natural language environment, such as a text-based game or dialogue system. Use natural language processing techniques to pre-process user inputs and generate agent responses. API implementation. Wrap the reinforcement learning agent with an API using a web framework like Flask or Django. Define endpoints that accept user text input and return the agent's responses or actions. Deployment. Deploy the API to a web server or cloud platform, making it accessible over the internet. Utilize containerization tools like Docker for portability and scalability. Role of natural language processing in API creation. Text pre-processing. Natural language processing techniques are used to pre-process user text input before feeding it into the reinforcement learning agent. This may involve tasks such as tokenization, lemmatization, and removing stop words. Response generation. NLP is employed to generate natural language responses or actions for the reinforcement learning agent based on its learned policy. This may involve techniques such as sequence-to-sequence modeling or template-based generation. Error handling. Natural language processing can help handle errors and ambiguities in user input by providing mechanisms for intent recognition, entity extraction, and context understanding. Challenges. Sparse rewards. Reinforcement learning in natural language processing tasks often faces the challenge of sparse or delayed rewards, where it may be difficult for the agent to learn an effective policy due to the complexity of language understanding and generation. Exploration versus exploitation. Balancing exploration, trying new actions, and exploitation, choosing actions with the highest expected reward in reinforcement learning with natural language processing can be challenging, especially in high dimensional action spaces. Sample efficiency. Reinforcement learning algorithms typically require large amounts of interaction data to learn effective policies, which can be costly or time consuming to collect in natural language processing tasks. Pros and cons. Pros. Integrating natural language processing with reinforcement learning enables artificial intelligence agents to interact with users through natural language interfaces, facilitating more intuitive and human-like communication. APIs for natural language processing with reinforcement learning provide a scalable and accessible way for developers to build language-driven artificial intelligence applications and services. Cons. Developing reinforcement learning agents for natural language processing tasks can be complex and require expertise in both reinforcement learning and natural language processing. Reinforcement learning in natural language processing may face challenges such as sparse rewards, exploitation trade-offs, and sample efficiency issues. By understanding the role of natural language processing in reinforcement learning, creating APIs for natural language processing tasks with reinforcement learning, and considering the associated challenges, pros and cons, students can gain valuable insights into the integration of language understanding and generation with reinforcement learning techniques. Modeling and deployment are essential aspects of building and implementing natural language processing systems with reinforcement learning. Let's delve into each phase in detail. Modeling. Define environment. Design the environment in which reinforcement learning agent will operate. For natural language processing tasks, this could be a dialogue system, text-based game, or virtual assistant. State representation. Define how textual inputs are represented as states in the reinforcement learning framework. This may involve techniques like word embeddings, bag of words representations, or more complex contextual embeddings. Action space. Define the possible actions the reinforcement learning agent can take based on the environment. In natural language processing tasks, Actions may include generating text responses, selecting from a set of predefined responses, or querying external knowledge bases. Reward function. Design a reward function that provides feedback to the reinforcement learning agent based on its actions. In natural language processing tasks, rewards could be based on user satisfaction, task completion, or other relevant metrics. Reinforcement learning algorithm selection. Choose an appropriate reinforcement learning algorithm for training the agent. Common algorithms for natural language processing tasks include deep Q learning, policy gradient methods, and actor critic methods. Training. Data collection. Collect data for training the reinforcement learning agent either through interactions with users or from existing datasets. Ensure that the data covers a diverse range of scenarios and user interactions. Training process. Train the reinforcement learning agent using the selected algorithm and the collected data. Monitor its performance and adjust hyperparameters as needed to improve learning efficiency and effectiveness. Evaluation. Evaluate the trained reinforcement learning agent on a separate validation set or through online testing to assess its performance and generalization ability. Iterate on the training process as necessary to improve performance. Deployment. Create API. Wrap the trained reinforcement learning agent with an API using a web framework like Flask or Django. Define endpoints that accept user inputs, that is, text queries, and return the reinforcement learning agent's response or actions. Containerization. Containerize the API using Docker to ensure portability and consistency across different deployment environments. This allows for easier deployment to cloud platforms or local servers. Deployment to cloud. Deploy the containerized API to a cloud platform such as AWS, GCP, or Azure. Utilize platform-specific services like AWS Elastic, Beanstalk, GCP App Engine, or Azure Container instances for deployment. Scaling and monitoring. Monitor the deployed API for performance metrics such as response time, throughput, and error rates. Implement scaling strategies to handle fluctuations in user demand and ensure optimal performance. Security. Implement security measures such as authentication, encryption, and access control to protect the API endpoints and user data. Regularly update and patch software components to mitigate security vulnerabilities. By following these steps for modeling and deployment, you can build and deploy NLP systems with reinforcement learning, providing intelligent and interactive language-driven applications and services. Decision tree. Integrating natural language processing with decision trees offer a structured approach to processing and analyzing textual data. Natural language processing sync with decision tree. Role of natural language processing in decision trees. Natural language processing techniques are used to pre-process and extract features from textual data, which are then fed into decision tree algorithms for classification or regression tasks. How natural language processing helps in decision trees. Natural language processing enables the conversion of unstructured text data into structured features that decision trees can process. This allows decision trees to make predictions or decisions based on the extracted linguistic information. Decision trees can use NLP-derived features to classify text documents into categorize, predict sentiment, or perform other tasks based on the semantic meaning of the text. Creating APIs for natural language processing with decision trees. Choose decision tree framework. Select a decision tree framework or library such as scikit, learn, or XGBoost that supports integration with NLP pre-processing techniques. Data pre-processing. Pre-process the text data using natural language processing techniques such as tokenization, lemmatization, and feature extraction. convert the text into numerical or categorical features that decision trees can understand. Model development. Train a decision tree model using the pre-processed text data. Define the classification or regression task based on the desired natural language processing application, that is, sentiment analysis, document classification. API implementation. Wrap the trained decision tree model with an API using a web framework like Flask or Django. Define endpoints that accept text input and return the model's predictions or classifications. Deployment. Deploy the API to a web server or cloud platform, making it accessible over the internet. Use containerization tools like Docker for portability and scalability. Role of natural language processing in API creation. Text pre-processing. Natural language processing techniques are used to pre-process user input or text data before feeding it into the decision tree model. This may involve tasks such as cleaning, tokenization, and feature extraction. Natural language processing provides methods for extracting relevant features from text data, such as word frequencies, n-grams, or semantic embeddings. These features serve as input to the decision tree model. Interpretability. Natural language processing techniques can help interpret the decision tree model's predictions by analyzing important features or splitting criteria driven from the text data. Challenges. High dimensional input space. Text data often results in high dimensional feature spaces, which can lead to overfitting and computational complexity in decision tree models. Data sparsity. Sparse text data, especially in applications like document classification, can pose challenges for decision tree models in effective learning patterns and making accurate predictions. Mobile interpretability. While decision trees are inherently interpretable models, interpreting their decisions in the context of natural language processing tasks can still be challenging due to the complexity of language processing. Pros and cons. Pros. Integrating natural language processing with decision trees offers a simple and interpretable approach to text classification and analysis. Decision trees are easy to understand and visualize, making them suitable for explaining model predictions to user or stakeholders. Cons. Decision tree may struggle with complex or nuanced language understanding tasks, especially compared to more sophisticated natural language processing models like deep learning architectures. Decision trees are prone to overfitting, especially in high-dimensional feature spaces, and may require careful tuning of hyperparameters to achieve optimal performance. By understanding the role of natural language processing in decision trees, creating APIs for natural language processing tasks with decision tree models, and considering the associated challenges, pros and cons, students can develop effective and interpretable text processing systems for a wide range of applications. Modeling and deployment are critical phases in building and implementing natural language processing (NLP) systems with decision trees. Modeling. Data pre-processing. Pre-process the text data using natural language processing techniques such as tokenization, stemming, and stop word removal. Convert the text into numerical or categorical features that decision trees can process. Feature engineering. Extract relevant features from the pre-processed text data. This may include bag of words representations, TF, IDF, term frequency, inverse document frequency, vectors, or word embeddings. Model selection. Choose an appropriate decision tree algorithm for the NLP task at hand. Common decision tree algorithms include CART, classification and regression trees, ID3, iterative decomizer 3, and C4-5. Model training. Train the selected decision tree model using the pre-processed text data. Tune hyperparameters such as tree depth, minimum samples per leaf, and splitting criteria to optimize model performance. Evaluation. Evaluate the trained decision tree model using validation data or cross-validation techniques. Measure performance metrics such as accuracy, precision, recall, and F1 score to assess the model's effectiveness deployment. Create API. Wrap the trained decision tree model with an API using a web framework such as Flask or Django. Define endpoints that accept text input and return the model's predictions or classifications. Containerization. Containerize the API using Docker to ensure portability and consistency across different deployment environments. This allows for easier deployment to cloud platforms or local servers. Deployment to cloud. Deploy the containerized API to a cloud platform such as AWS, GCP, or Azure. Utilize platform-specific services like AWS Elastic Beanstalk, Google App Engine, or Azure Container instances for deployment. Scaling and monitoring. Monitor the deployed API for performance metrics such as response time, throughput, and error rates. Implement scaling strategies to handle functions in user demand and ensure optimal performance. Security. Implement security measures such as authentication, encryption, and access control to protect the API endpoints and user data. Regularly update and patch software components to mitigate security vulnerabilities by following these steps for modeling and deployment. You can build and deploy natural language processing systems with decision trees, providing efficient and interpretable solutions for text classification and analysis tasks. SVM, integrating natural language processing with support vector machines. SVM offers a powerful approach to text classification and sentiment analysis tasks. Natural language processing sync with SVM. Role of NLP in SVM. Natural language processing techniques pre-process and transform text data into numerical feature representations, which are then fed into SVM algorithms for classification tasks. Natural language processing helps extract meaningful features from text, making it suitable for support vector machine classification. How natural language processing helps in support vector machine. Natural language processing enables the conversion of raw text data into structured feature vectors that SVMs can process. Features extracted from text data can include word frequencies, n-grams, or TF-IDF scores. SVMs utilize these feature vectors to find an optimal hyperplane that separates different classes or categories in the feature space, making them well suited for text classification tasks. Creating APIs for natural language processing with SVM. Choose natural language processing library. Select an natural language processing library or toolkit such as NLTK, Spacy, or scikit-learn for pre-processing and feature extraction. Data pre-processing. Pre-process the text data using natural language processing techniques such as tokenization, stemming, and stop word removal. Convert the text into numerical feature representations suitable for SVM input. Model training. Train an SVM classifier using the pre-processed text data and the extracted feature vectors. The hyperparameters such as the choice of kernel, that is linear, polynomial, radial basis function, and regularization parameter. API implementation. Wrap the trained SVM classifier with an API using a web framework like Flask or Django. Define endpoints that accept text input and return the SVM's predictions or classifications. Deployment. Deploy the API to a web server or cloud platform, making it accessible over the internet. Use containerization tools like Docker for portability and scalability. Role of natural language processing in API creation. Text pre-processing. NLP techniques pre-process user input or text data before feeding it into the SVM classifier. This involves tasks such as cleaning, tokenization, and feature extraction. Feature extraction. Natural language processing provides methods for extracting relevant features from text data such as word frequencies, n-grams, or semantic embeddings. These features serve as input to the SVM classifier. Interpretability. Natural language processing techniques can help interpret the SVM classifier's decision by analyzing important features or support vectors derived from the text data. Challenges. High-dimensional feature space. Text data often results in high-dimensional feature spaces, which can lead to overfitting and computational complexity in SVM classifiers. Data sparsity. Sparse text data, especially in applications like document classification, can pose challenges for SVM classifiers in effectively learning decision boundaries and making accurate predictions. Kernel selections. Choosing the appropriate kernel function and tuning its parameters can be challenging, as different kernels may perform differently on different text datasets. Pros and cons. Pros. Integrating natural language processing with SVM provides a robust and effective approach to text classification and sentiment analysis tasks. SVM classifiers are well suited for handling high-dimensional feature spaces and can learn complex decision boundaries from text data. Cons. SVM classifiers may struggle with large-scale text data sets due to computational complexity and memory requirements. SVMs may not perform well on highly imbalanced or noisy text data, requiring careful pre-processing and hyperparameter tuning. By understanding the role of natural language processing in SVM, creating APIs for NLP tasks with SVM classifiers, and considering the associated challenges, pros and cons, students can develop effective and scalable solutions for text classification and sentiment analysis tasks. Modeling and deployment are key stage in building and implementing natural language processing systems with support vector machines. Modeling. Data pre-processing. Pre-process the text data using natural language processing techniques such as tokenization, stemming, and stop word removal. Convert the text into numerical feature representations suitable for SVM input. Feature engineering. Extract relevant features from the pre-processed text data. This could include bag of words, representations, TF-IDF, term frequency, inverse document frequency, vectors, or word embeddings. Model selection. Choose the appropriate SVM variant, that is linear SVM, polynomial SVM, or radial basis function SVM, based on the nature of the text classification problem and the characteristics of the dataset. Hyperparameter tuning. Tune hyperparameters such as the regularization parameter and kernel parameters, gamma for RBF kernel, degree for polynomial kernel, using techniques like grid search or random search. Model training. Train the selected SVM model using the pre-processed text data and the extracted feature vectors. Deployment. API creation. Wrap the trained SVM model with an API using a web framework such as Flask or Django. Define endpoints that accept text input and return the SVM's predictions or classifications. Containerization. Containerize the API using Docker to ensure portability and consistency across different deployment environments. This facilitates easy deployment to cloud platform or local servers. Deployment to cloud. Deploy the containerized API to a cloud platform such as AWS, Google Cloud Platform, or Microsoft Azure. Use platform-specific services like AWS Elastic Beanstalk, Google App Engine, or Azure App Service for deployment. Scaling and monitoring. Monitor the deployed API for performance metrics such as response time, throughput, and error rates. Implement scaling strategies to handle fluctuations in used demand and ensure optimal performance. Security. Implement security measures such as authentication, encryption, and access control to protect the API endpoints and user data. Regularly update and patch software components to mitigate security vulnerabilities. By following these steps for modeling and deployment, you can build and deploy natural language processing systems with support vector machines, providing efficient and effective solutions for text classification and sentiment analysis tasks. Clustering. Integrating natural language processing with clustering algorithms offers a powerful approach to discover patterns and group similar text documents together. Natural language processing sync with clustering. Role of natural language processing in clustering. NLP techniques pre-process text data and extract relevant features which are then used by clustering algorithms to group similar documents together based on their semantic similarity. How NLP helps in clustering. Natural language processing enables the transformation of raw text data into numerical feature representations such as TF-IDF vectors or word embeddings, which are suitable for clustering algorithms. Natural language processing techniques capture the semantic meaning of text documents, allowing clustering algorithms to identify groups of documents with similar topics, themes, or content. Creating APIs for natural language processing with clustering. Choose natural language processing library. Select an NLP library or toolkit such as NLTK, Spacy, or scikit-learn for pre-processing and feature extraction. Data pre-processing. Pre-process the text data using natural language processing techniques such as tokenization, stemming, and stop word removal. Convert the text in numerical feature representations suitable for clustering. Feature extraction. Extract relevant features from the pre-processed text data using techniques such as TF-IDF word embeddings, that is word to vec, glove, or topic modeling, that is latent Dirichlet allocation. Clustering algorithm selection. Choose an appropriate clustering algorithm such as k-means, hierarchical clustering, or dbScan based on the characteristics of the text data and the desired clustering outcomes. Model training. Train the selected clustering algorithms using the pre-processed text data and the extracted feature vectors. Role of NLP in API creation. Text pre-processing. NLP techniques pre-process user input or text data before feeding it into the clustering algorithm. This involves tasks such as cleaning, tokenization, and feature extraction. Feature extraction. NLP provides methods for extracting relevant features from text data such as word frequencies, semantic embeddings, or topic distributions. These features serve as input to the clustering algorithm. Interpretability. Natural language processing techniques can help interpret the clusters generated by the clustering algorithm by analyzing the most representative features or keywords within each cluster. Challenges. High-dimensional feature space. Text data often results in high-dimensional feature spaces, which can pose challenges for clustering algorithms in terms of computational complexity and memory requirements. Interpretability. Interpreting the cluster generated by clustering algorithms in the context of text data can be challenging, especially when dealing with high-dimensional feature spaces and complex semantic relationships. Choosing the right number of clusters. Selecting the optimal number of cluster for a given text dataset is a non-trivial task and may require domain knowledge or experimentation. Pros. Integrating NLP with clustering provides a data-driven approach to discovering patterns and grouping similar text documents together. Clustering algorithms can uncover hidden structures within text data and facilitate exploratory analysis and knowledge discovery. Cons. Clustering algorithms may struggle with high-dimensional and sparse text data, leading to suboptimal cluster quality and interpretability. Determining the optimal number of clusters and evaluating the quality of clusters generated by clustering algorithms can be challenging, especially in the absence of ground truth labels. By understanding the role of natural language processing in clustering, creating APIs for natural language processing tasks with clustering algorithms, and considering the associated challenges, pros and cons, students can develop effective and scalable solution for text clustering and exploratory analysis tasks. Modeling and deployment are essential stages in building and implementing natural language processing systems with clustering algorithms. Let's explore each step in detail. Modeling. Data pre-processing. Pre-process the text data using natural language processing techniques such as tokenization, stemming, and stop word removal. Convert the text into numerical feature representations suitable for clustering algorithms. Feature extraction. Extract relevant features from the pre-processed text data using techniques such as TF-IDF, term frequency inverse, document frequency, word embeddings, that is word to vec globe, or topic modeling, that is latent Dirichlet allocation. Clustering algorithm selection. Choose an appropriate clustering algorithm based on the characteristics of the text data and the desired clustering outcome. Common clustering algorithms for text data include k-means, hierarchical clustering, and dbScan. Hyperparameter tuning. Tune hyperparameters of the selected clustering algorithm, such as the number of clusters, k-form, k-means, linkage criteria for hierarchical clustering, or neighborhood size for dbScan. Model training. Train the selected clustering algorithm using the pre-processed text data and the extracted feature vectors. Deployment. API creation. Wrap the trained clustering model with an API using a web framework such as Flask or Django. Define endpoints that accept text input and return the clusters or cluster assignments for each input text. Containerization. Containerize the API using Docker to ensure portability and consistency across different deployment environments. This facilitates deployment to cloud platforms or local servers. Deployment to cloud. Deploy the containerized API to a cloud platform such as AWS, Google Cloud Platform, or Microsoft Azure. Utilize platform-specific services like AWS Elastic Beanstalk, Google Kubernetes Engine, or Azure App Service for deployment. Scaling and monitoring. Monitor the deployed API for performance metrics such as response time, throughput, and error rates. Implement scaling strategies to handle functions in user demand and ensure optimal performance. Security. Implement security measures such as authentication, encryption, and access control to protect the API endpoints and user data. Regularly update and patch software components to mitigate security vulnerabilities. By following these steps for modeling and deployment, you can build and deploy NLP systems with clustering algorithms, providing efficient and effective solutions for text clustering and exploratory analysis tasks. Data mining. Data mining plays a crucial role in natural language processing by providing methods and techniques for extracting valuable insights and patterns from large volumes of text data. Text data pre-processing. Before any natural language processing task, text data often needs pre-processing. Data mining techniques such as tokenization, stemming, and lemmatization help in transforming raw text into a format suitable for natural language processing analysis. Feature extraction. Data mining methods are employed to extract relevant features from text data. These features could include word frequencies, n-grams, syntactic patterns, or semantic representations, which are then used as inputs for natural language processing algorithms. Text classification. In tasks like sentiment analysis, spam detection, or topic categorization, data mining techniques such as classification algorithms, that is decision trees, sport vector machines, or neural networks, are applied to labeled text data to learn patterns and make predictions. Information retrieval. Data mining helps in retrieving relevant information from large text corpora. Techniques like text indexing, keyword extraction, and relevance ranking are employed to efficiently search and retrieve documents matching a user's query. Entity recognition and named entity recognition, NER. Natural language processing applications often involve identifying entities such as names of people, organizations, locations, etc. Data mining methods, particularly supervised learning algorithms, are used to recognize and classify these entities within text. Text clustering and topic modeling. Clustering algorithms like k-means or hierarchical clustering, along with topic modeling techniques such as latent Dirichlet allocation (LDA) or non-negative matrix factorization (NMF) are employed to discover hidden patterns and group similar documents together based on their content. Text summarization. Data mining techniques aid in summarizing large volumes of text by extracting the most important sentences or passages. Methods like extractive summarization use algorithms to identify and select key information from the original text. Language generation. In tasks such as machine translation or text generation, data mining plays a role in learning patterns from large bilingual or multilingual corpora. Techniques like neural machine translation leverage data mining principles to generate coherent and contextually appropriate translations or text outputs. Bayesian network. Bayesian network plays a significant role in natural language processing by providing a probabilistic framework for modeling uncertainty and dependencies among linguistic elements. Language modeling. Bayesian networks can be used to model the probability distribution of sequences of words or phrases in a language. This is essential for tasks like speech recognition, machine translation, and text generation, where understanding the likelihood of certain word sequences is crucial. Part of speech tagging. In natural language processing, part of speech tagging assign grammatical categories, nouns, verbs, adjectives, etc. to words in a sentence. Bayesian networks can model the conditional dependencies between words and their possible parts of speech, allowing for more accurate tagging based on context. Named entity recognition. Bayesian networks can model the relationships between words in a sentence and the likelihood of them being part of named entities such as people's name, locations, organizations, etc. This aids in the task of NER, where identifying and classifying named entities is essential. Sentiment analysis. In sentiment analysis, Bayesian networks can model the relationships between words or phrases and the sentiment expressed in a text by considering the conditional probabilities of different words given a particular sentiment class. Bayesian networks can classify text into positive, negative, or neutral sentiment categories. Text classification. Bayesian networks are used in text classification tasks such as topic categorization, spam detection, or document classification. By modeling the dependencies between words or features and the classes of documents, Bayesian networks can assign probabilities to different classes for a given input text. Dependencies parsing. Dependencies parsing involves analyzing the grammatical structure of sentences to identify syntactic dependencies between words. Bayesian networks can represent the probabilistic relationships between words and their syntactic dependencies, aiding in accurate parsing of complex sentences. Machine translation. Bayesian networks can model the conditional probabilities of translations between language, which is essential for machine translation systems, by considering the likelihood of different translations given a source language input. Bayesian networks help in generating accurate translations. Information extraction. Bayesian networks can assist in extracting structured information from unstructured text by modeling the dependencies between words or phrases and the types of information to be extracted, that is, dates, locations, quantities. This aids in tasks such as extracting events from news articles or extracting product specifications from product descriptions. In summary, Bayesian networks provide a powerful framework for probabilistic modeling in natural language processing, allowing for the representation of complex relationships and uncertainties inherent in natural language data. They are versatile tools that can be applied across various natural language processing tasks to improve accuracy and performance. Evolutionary algorithms. Evolutionary algorithms play a crucial role in natural language processing by providing powerful optimization techniques for solving complex problems such as language modeling, text generation, and feature selection. Language modeling and generation. Evolutionary algorithm can be used to evolve language models that capture the underlying structure and patterns of natural language. By treating language generation as an optimization problem, evolutionary algorithms can search for the most probable sequence of words given a context, leading to improved text generation systems. Text summarization. Evolutionary algorithms can optimize the process of text summarization by selecting the most informative sentences or phrases from a document while preserving its essential meaning. This is achieved by evolving selection criteria that prioritize sentences based on their relevance and importance. Feature selection and dimensionality reduction. In natural language processing tasks such as text classification or sentiment analysis, feature selection is crucial for improving model performance and reducing computational complexity. Evolutionary algorithms can efficiently search through a large space of features and select the most discriminative ones, leading to more accurate and efficient natural language processing models. Neural architecture search (NAS). With the rise of deep learning in natural language processing, designing optimal neural network architectures has become increasingly important. EAS can be employed to search for effective neural architecture for tasks such as machine translation, text classification, and named entity recognition. By evolving architectures that maximize performance on a given task, EAS enable the discovery of novel network designs that outperform handcrafted architectures. Parameter tuning and optimization. EAS can optimize the hyperparameters of natural language processing models such as learning rates, regularization strengths, and network architectures. By evolving sets of hyperparameters that maximize performance on a validation set, EAS enable the automatic fine-tuning of NLP models, leading to improved accuracy and robustness. Word embedding learning. Word embeddings play a fundamental role in many natural language processing tasks by representing words as dense, low-dimensional vectors. EAS can be used to learn word embeddings by optimizing their representations based on contextual information from large text corpora. By evolving embeddings that capture semantic similarities and relationships between words, EAS improve the performance of downstream natural language processing tasks such as semantic similarity measurement and word sense disambiguation. Semantic parsing and natural language understanding. Evolutionary algorithms can optimize the process of semantic phrasing, which involves converting natural language expressions into formal representations such as logical forms of semantic graphs. By evolving parsers that accurately capture the meaning of natural language inputs, EAS facilitate the development of robust natural language understanding systems for applications such as question answering and dialogue systems. In summary, evolutionary algorithms provide versatile optimization techniques for addressing a wide range of challenges in natural language processing, including language modeling, text generation, feature selection, and neural architecture search. By harnessing the power of evolution, these algorithms enable the automatic discovery of effective solutions to complex natural language processing problems, leading to significant advancements in the field. Pattern recognition. Pattern recognition plays a fundamental role in natural language processing by enabling machine to identify and interpret patterns within textual data. Named entity recognition. Pattern recognition techniques are used to identify and classify named entities such as person names, organization names, locations, dates, and numerical expressions within text. NER systems employ pattern matching algorithms, statistical models, or machine learning approaches to recognize these entities based on patterns in the text and contextual information. Part of speech tagging, POS. POS tagging involves assigning grammatical categories such as noun, verb, adjective to words in a sentence. Pattern recognition methods analyze the syntactic structure of sentences and identify recurring patterns that correlate with specific parts of speech. Machine learning algorithms including hidden Markov models, HMMS, and conditional random fields, CRFS, are commonly used for POS tagging, leveraging patterns in labeled training data to make predictions. Sentiment analysis. In sentiment analysis, pattern recognition is used to classify the sentiment expressed in text as positive, negative, or neutral. This involves identifying linguistic patterns such as specific words, phrases, or syntactic structures that convey sentiment polarity. Supervised learning algorithms such as support vector machines or recurrent neural networks learn to recognize these patterns from labeled data and predict sentiment in unseen text. Text classification. Pattern recognition techniques are applied to categorize documents into predefined classes or topics based on the patterns present in the text. Document classification algorithms analyze textual features and learn patterns that discriminate between different classes. Methods such as naive Bayes, decision trees, and neural networks learn to recognize discriminative patterns from labeled training data and classify new documents accordingly. Topic modeling. Topic modeling algorithms such as latent Dirichlet allocation LDA aim to discover latent topic present in a collection of documents. These algorithms identify patterns of word co-occurrence across documents and cluster words into topic based on these patterns. By recognizing common patterns in word distributions, topic modeling enables the unsupervised discovery of underlying themes or topics in textual data. Text clustering. Pattern recognition is used in text clustering to group similar documents together based on patterns in their content. Clustering algorithms analyze textual features and identify patterns of similarity or dissimilarity between documents. Techniques such as k-means clustering or hierarchical clustering recognize patterns in document representations and group related documents into clusters accordingly. Dependency parsing. Dependency parsing involves analyzing the syntactic structure of sentences to identify grammatical relationships between words. Pattern recognition methods analyze patterns of word dependencies and syntactic structures to parse sentences into dependency trees. Dependency parsing algorithms employ pattern matching and statistical models to recognize recurring patterns of syntactic relationships in text. Information extraction. Pattern recognition techniques are used in information extraction tasks to identify structured information from unstructured text. Information extraction systems analyze patterns in text and extract relevant entities, relationships, or events based on predefined patterns or rules. These systems employ pattern matching algorithms, regular expressions, or machine learning approaches to recognize and extract structured information from textual data. In summary, pattern recognition is integral to many tasks in natural language processing, including named entity recognition, part of speech tagging, sentiment analysis, text classification, topic modeling, text clustering, dependency parsing, and informative extraction. By identifying and interpreting patterns within textual data, pattern recognition enables machines to understand and process natural language effectively. Computer vision. Computer vision and natural language processing are two distinct fields of artificial intelligence, but their integration can lead to powerful synergies and enhance various applications. Multimodal understanding. Combining visual information from images or videos with textual data enables machines to have a more comprehensive understanding of the world. By incorporating visual context into NLP tasks, such as sentiment analysis, summarization, or translation, models can make more informed decisions and provide richer outputs. Visual question answering. VQA. VQA is a task that involves answering questions about image using natural language. By leveraging both computer vision and natural language processing techniques, VQA systems can analyze images and generate text-based answers to questions, facilitating human-like interaction with visual data. Image captioning. Image captioning is the process of automatically generating textual descriptions for images by combining computer vision for image understanding and natural language processing for language generation. Image captioning systems can produce accurate and descriptive captions that capture the visual content of images. Sentiment analysis, visual data. Sentiment analysis traditionally focuses on analyzing text to determine the sentiment expressed within it. However, with the rise of social media and the proliferation of visual content, sentiment analysis can be enhanced by incorporating visual cues from images or videos, allowing for a more nuanced understanding of sentiment. Cross-model retrieval. Cross-model retrieval involves searching for multimedia content across different modalities, such as finding images based on textual queries or vice versa. By integrating computer vision and natural language processing techniques, cross-model retrieval systems can bridge the gap between visual and textual data, enabling users to search for content more effectively. Document understanding. In applications such as document analysis and understanding, incorporating visual information from documents, that is, scanned images or PDFs, can enhance natural language processing tasks such as text extraction, entity recognition, and semantic analysis. Computer vision techniques can be used to pre-process and extract relevant visual features from documents, which can then be combined with textual analysis to improve overall understanding. Visual semantic embeddings aim to learn joint representations of image and text in a shared embedding space. By aligning visual and textual features, these embeddings enable cross-modal tasks such as image text retrieval, image annotation, and image search, where visual and textual information can be seamlessly integrated and compared. Accessibility and assistive technologies. Integrating computer vision and natural language processing can lead to the development of assistive technologies for individuals with visual impairments. By converting visual content into textual descriptions or providing audio-based feedback, these technologies can make visual information more accessible and inclusive. In summary, the importance of computer vision in natural language processing lies in its ability to enrich textual understanding with visual context, enable multimodal interaction, enhance sentiment analysis on visual data, facilitate cross model retrieval, improve document understanding, learn joint representations of images and text, and develop assistive technologies for accessibility. By integrating computer vision and natural language processing techniques, we can unlock new possibilities for understanding and interacting with visual and textual data in more intelligent and human-like ways. Export system. In the context of natural language processing, an export system typically refers to the process of deploying or making natural language processing models and systems accessible for use in real-world applications. Accessibility. Export systems make natural language processing models and systems accessible to end users, developers, and organizations who may not have the expertise or resources to develop natural language processing solutions from scratch. By providing pre-trained models, APIs, or software libraries, export systems democratize access to natural language processing technology and enable broader adoption. Scalability. Export systems facilitate the scalability of natural language processing solutions by allowing them to be deployed in various environments, including cloud platforms, edge devices, or on-premises servers. This scalability enables natural language processing applications to handle large volumes of data, serve multiple users concurrently, and adapt to changing demands. Integration. Export systems enable the integration of natural language processing capabilities into existing software applications, workflows, and systems. By providing well-documented APIs, SDKs, or integration tools, export systems make it easier for developers to incorporate natural language processing functionality seamlessly into their products and services. Interoperability. Export systems promote interoperability by supporting standard formats and protocols for exchanging natural language processing data and models. This interoperability allows natural language processing solutions to work across different platforms, programming languages, and frameworks, enhancing flexibility and compatibility. Update and maintenance. Export systems facilitate the update and maintenance of natural language processing models and systems by providing mechanisms for versioning, deployment, and monitoring. This ensures that natural language processing solutions remain up to date with the latest advancements, bug fixes, and performance improvements over time. Security and compliance. Export systems address security and compliance requirements by implementing authentication, authorization, encryption, and other security measures to protect sensitive data and ensure regulatory compliance. This is particularly important for natural language processing applications handling personal, confidential, or regulated information. Performance optimization. Export systems enable performance optimization by providing tools and techniques for optimizing natural language processing models and systems for speed, memory usage, and resource efficiency. This optimization ensures that natural language processing applications deliver fast and responsive user experiences while minimizing resource consumption. Monetization. Export systems offer opportunities for monetization by providing natural language processing solutions as commercial products, services, or subscriptions. This allows developers and organizations to generate revenue from their NLP innovations and investments, driving innovation and sustainability in the field. In summary, export systems play a critical role in the deployment, accessibility, scalability, integration, interoperability, update and maintenance, security and compliance, performance optimization, and monetization of natural language processing models and systems, enabling their practical use in real-world applications across diverse domains and industries. Robotics. Robotics and natural language processing have a symbiotic relationship where advancements in one field and significantly benefit the other. Human-robot interaction (HRI). Robotics provide a tangible platform for applying natural language processing techniques in real-world scenarios. Natural language processing enables robots to understand and respond to human commands, questions, and gestures, enhancing the quality of interaction between humans and robots. This is crucial for various applications, including personal assistants, customer service robots, and collaborative robots (COBOTS) in industrial settings. Natural language interface. Robotics leverages natural language processing to develop natural language interfaces that enable users to interact with robots using spoken or written language. Natural language processing techniques such as speech recognition, natural language understanding, and dialogue management allow robots to comprehend and respond to human language inputs, making human-robot communication more intuitive and efficient. Task understanding and execution. Natural language processing enables robots to understand complex instructions and commands given in natural language. By parsing and analyzing textual inputs, robots can extract relevant information and perform tasks autonomously or collaboratively with humans. This is particularly useful in applications such as home automation, logistics, healthcare, and manufacturing. Personalized assistance. Robotic combined with NLP can provide personalized assistance tailored to individual users' needs and preferences. By analyzing natural language inputs and user interactions, robots can adapt their behavior, responses, and recommendations to better serve users in various contexts, such as smart homes, elder care, education and entertainment, information retrieval, and knowledge acquisition. Natural language processing enables robots to access and retrieve information from large textual databases, knowledge bases, or the internet. By leveraging techniques such as information extraction, text summarization, and semantic search, robots can gather relevant information to answer user queries, perform tasks, or make informed decisions in real time. Collaborative problem solving. Robotics and natural language processing can facilitate collaborative problem solving between humans and robots by enabling robots to understand and generate natural language descriptions of tasks, environments, and constraints. Natural language processing enhances communication and coordination in collaborative robotics applications, leading to more effective teamwork and task completion. Language learning and adaptation. Natural language processing techniques can help robots learn and adapt to new languages, dialects, or communication styles over time. By analyzing linguistic patterns and feedback from interactions with users, robots can improve their language understanding and generation capabilities through machine learning and reinforcement learning techniques. Social and emotional interaction. Robotics integrated with natural language processing can enhance social and emotional interaction between robots and humans. By analyzing sentiment, tone, and context in natural language inputs, robots can exhibit empathy, humor, and emotional intelligence in their responses and behaviors, fostering more meaningful and engaging interactions with users. In summary, robotics plays a crucial role in applying and advancing natural language processing techniques in real-world applications, enabling robots to understand and respond to human language inputs, perform tasks autonomously, provide personalized assistance, retrieve information, collaborate with humans, learn new languages, and engage in social and emotional interactions. This interdisciplinary synergy between robotics and natural language processing holds great promise for shaping the future of human-robot interaction and collaboration in diverse domains. Speech recognition. Speech recognition is a foundational component of natural language processing with several key importance. Accessibility. Speech recognition technology makes digital devices and applications accessible to individuals with disabilities or those who are unable to use traditional input methods such as typing. It enables users to interact with computers, smartphones, and other devices using spoken language, opening up opportunities for inclusion and participation in various digital activities. Convenience. Speech recognition enhances user convenience by enabling hands-free and eyes-free interaction with devices and applications. Users can dictate text, issue commands, and control software using voice commands, allowing for seamless multitasking and improved productivity in various contexts, such as driving, cooking, or working out. Natural interaction. Speech recognition enables more natural and intuitive interaction between humans and machines. By understanding spoken language inputs, devices and applications can emulate human-like communication, making interactions more conversational and engaging for users. This natural interaction paradigm is particularly valuable for virtual assistants, smart speakers, and chatbots. Efficiency. Speech recognition improves efficiency by enabling rapid and accurate input of text and commands. Users can dictate text more quickly than typing, especially for long documents or messages, reducing the time and effort required for data entry. This efficiency gain is particularly beneficial in scenarios where typing is impractical or cumbersome. Multimodal interaction. Speech recognition facilitates multimodal interaction by integrating with other modalities such as text, images, and gestures. Combined with other natural language processing techniques such as natural language understanding and dialogue management, speech recognition enables richer and more contextually aware interactions, enhancing the overall user experience. Personalization. Speech recognition technology enables personalized user experiences by recognizing individual voices and preferences. By adapting to users' speech patterns, accents, and vocabulary, speech recognition systems can improve accuracy and tailor responses to better meet users' needs and preferences over time. Accessibility for low literate users. Speech recognition technology can benefit individuals with low literacy levels or limited access to written language by allowing users to communicate verbally. Speech recognition enables access to information, services, and opportunities that may otherwise be challenging to access through traditional written communication channels. Automation and voice-controlled interfaces. Speech recognition powers voice-controlled interfaces and automation systems in various domains, including home automation, automotive, healthcare, and industrial applications. By integrating with voice-enabled devices and platforms, speech recognition enables hands-free control and automation of tasks, improving efficiency and safety in diverse settings. In summary, speech recognition is a critical component of natural language processing that enhances accessibility, convenience, natural interaction, efficiency, multimodal interaction, personalization, accessibility for low literate users, and automation in various applications and domains. Its importance lies in enabling seamless and intuitive communication between humans and machines, driving innovation and improving user experiences in the digital age. Genetic algorithms. Genetic algorithms, GAS, play a significant role in natural language processing by providing powerful optimization techniques for solving complex problems and improving the performance of natural language processing systems. Here is why generic algorithms are important in natural language processing. Feature selection and optimization. Genetic algorithms can optimize feature sets for natural language processing tasks such as text classification, sentiment analysis, and named entity recognition by selecting the most relevant features from a large pool of candidates. GAS improve the efficiency and effectiveness of natural language processing models, leading to better performance. Hyperparameter tuning. Genetic algorithms can optimize the hyperparameters of natural language processing models such as learning rates, regularization strengths, and network architectures. By exploring the hyperparameter space and evolving better configurations, GAS enhance the robustness and generalization ability of natural language processing models. Text generation. Genetic algorithms can be used to evolve language models for text generation tasks such as machine translation, dialogue generation, and story generation. By evolving models that generate coherent and contextually appropriate text, GAS enable the creation of more realistic and engaging natural language processing applications. Optimization of rule-based systems. In rule-based natural language processing systems, genetic algorithms can optimize the rules and parameters used for tasks such as parsing, information extraction, and text summarization. By evolving rules that capture the underlying patterns in text data, genetic algorithms improve the accuracy and efficiency of rule-based natural language processing systems. Language model adaptation. Genetic algorithms can adapt pre-trained language models to specific domains or tasks by fine-tuning their parameters on domain-specific data. By evolving models that better capture the linguistic characteristics of the target domain, genetic algorithms enhance the performance of natural language processing applications in specialized domains such as finance, healthcare, or legal. Optimization of neural network architectures. Genetic algorithms can optimize the architectures of neural networks used in natural language processing tasks such as sentiment analysis, text classification, and sequence labeling. By evolving architectures that are better suited to the characteristics of the input data and the requirements of the task, genetic algorithms improve the performance of neural natural language processing models. Ensemble learning. Genetic algorithm can be used to optimize the combination of multiple natural language processing models or classifiers through ensemble learning. By evolving ensembles that combine the strengths of individual models, GAS enhance the robustness and accuracy of natural language processing systems, particularly in tasks with high variability of uncertainty. Automatic problem solving. Genetic algorithms can automatically search for solutions to complex natural language processing problems without requiring explicit problem-specific knowledge or manual intervention. By evolving solutions through iterative selection, crossover, and mutation operations, GAS enable the automatic discovery of effective strategies for tackling natural language processing challenges. In summary, genetic algorithms are important in natural language processing for optimizing feature sets and hyperparameters, evolving language models, optimizing rule-based systems, adapting language models to specific domains, optimizing neural network architectures, enabling ensemble learning, and facilitating automatic problem solving. Their ability to efficiently search large solution spaces and find effective solutions makes them valuable tools for advancing natural language processing research and applications. Swarm intelligence. Swarm intelligence techniques inspired by the collective behavior of social insects and other natural systems offer unique advantages in solving optimization and decision-making problems in natural language processing. Here is why swarm intelligence is important in natural language processing. Optimization of natural language processing models. Swarm intelligence algorithms such as particle swarm optimization (PSO) and ANT colony optimization (ACO) can optimize the parameters and structures of natural language processing models. These algorithms efficiently explore large solution spaces and find near optimal solution for tasks like feature selection, hyperparameter tuning, and neural network optimization. Text clustering and topic modeling. Swarm intelligence algorithms can cluster similar documents or topics in large text corpora. Techniques like ant colony clustering or particle swarm clustering leverage the collective behavior of agents to partition documents into cohesive clusters based on similarities in their content, enabling effective text organization and topic discovery. Document summarization. Swarm intelligence can aid in document summarization by selecting the most representative sentences or passages from a document or collection of documents. Algorithms like ant colony optimization or bee colony optimization can identify key information and generate concise summaries that capture the essence of the original text, facilitating information retrieval and understanding. Semantic parsing and natural language understanding. Swarm intelligence techniques can enhance semantic parsing and understanding of natural language expressions by leveraging swarm-based search strategies. These algorithms can explore the space of possible semantic interpretations and infer the meaning of ambiguous or complex language constructs, more effectively improving the accuracy of natural language processing systems. Language model adaptation. Swarm intelligence algorithms can adapt pre-trained language models to specific tasks or domains by fine-tuning their parameters. Techniques like particle swarm optimization or bacterial foraging optimization can optimize the weights and connections of neural language models on task-specific data, enabling better performance and generalization in specialized natural language processing applications. Named entity recognition. Swarm intelligence can improve named entity recognition by optimizing the selection and ranking of candidate entities in text. Algorithms like ant colony optimization or Firely algorithm can explore the space of possible entity candidates and assign confidence scores based on contextual information, leading to more accurate identification of named entities in natural language processing tasks. Sentiment analysis and opinion mining. Swarm intelligence techniques can aid in sentiment analysis and opinion mining by aggregating opinions and sentiments for multiple sources of text. Algorithms like ant colony optimization or BAT algorithm can analyze textual data from social media, reviews, or surveys and extract sentiment patterns or trends, providing valuable insights into public opinion and user preferences. Cross-linguistic analysis and translation. Swarm intelligence can facilitate cross-linguistic analysis and machine translation by aligning and mapping language representations across different languages. Techniques like particle swarm optimization or bee colony optimization can learn translation mappings and alignments from bilingual or multilingual text corpora, enabling accurate and efficient translation between languages in natural language processing systems. In summary, swarm intelligence offers valuable techniques for optimizing natural language processing models, clustering and topic modeling, document summarization, semantic parsing, language model adaptation, named entity recognition, sentiment analysis, opinion mining, cross-linguistic analysis, and translation. By harnessing the collective behavior of swarms, these algorithms provide efficient and effective solutions to complex natural language processing challenges, advancing research and applications in the field. Transfer learning. Natural language processing and transfer learning are closely related in the context of machine learning and deep learning. Importance of natural language processing. Natural language processing focuses on enabling computers to understand, interpret, and generate human language in a way that is both meaningful and useful. It encompasses a range of tasks such as language translation, sentiment analysis, named entity recognition, and text summarization. Natural language processing has numerous applications across various industries, including healthcare, finance, customer service, and more. Importance of transfer learning. Transfer learning involves leveraging knowledge gained while solving one problem and applying it to a different but related problem. It has become increasingly important in deep learning because it allows models to be trained on large datasets for one task and then adapted or fine-tuned for another task with a smaller dataset. This is especially useful when labeled data for the target task is limited or expensive to obtain. Pre-trained language models. In natural language processing, pre-trained language model like BERT, bidirectional encoder representations from transformers, GPT, generative pre-trained transformer, and their variants have revolutionized the field. These models are trained on large text corpora using unsupervised learning and then fine-tuned for specific NLP tasks using transfer learning. Transfer learning for NLP tasks. Transfer learning allows NLP models to benefit from the knowledge learned during pre-trained when solving downstream tasks. For example, a pre-trained BERT model can be fine-tuned for tasks such as sentiment analysis or question answering with relatively small amounts of labeled data specific to those tasks. Domain adaptation. Transfer learning is also used in NLP for domain adaptation, where a model trained on data from one domain is adapted to perform well on data from a different domain. For example, a sentiment analysis model trained on product reviews might be fine-tuned for analyzing sentiment in social media posts. Multitask learning. Another link between NLP and transfer learning is multitask learning, where a single model is trained to perform multiple NLP tasks simultaneously. Transfer learning facilitates multitask learning by allowing the model to transfer knowledge from one task to another, leading to improved performance on all tasks. Advancing the state of the art in NLP. Transfer learning has significantly contributed to pushing the boundaries of what NLP models can achieve. By allowing models to transfer knowledge from one domain or task to another, transfer learning has facilitated the development of more sophisticated and capable NLP models. Leveraging knowledge from pre-training. Pre-trained language models are trained on large amounts of text data using unsupervised learning techniques. During this pre-training phase, the model learns general language representations and captures intricate patterns and relationships in the text. Transfer learning allows NLP models to leverage this knowledge, which is encoded in the parameters of the pre-trained model. Adapting to specific tasks or domains. While pre-trained models have a general understanding of language, they may not perform optimally on specific tasks or domains without further adaptation. Transfer learning enables fine-tuning or adaptation of pre-trained models for specific tasks or domains by exposing them to task-specific or domain-specific labeled data. Achieving better performance with less labeled data. An important challenge in NLP is the scarcity of labeled data for specific tasks or domains, which is often required to train supervised models effectively. Transfer learning mitigates this challenge by allowing models to leverage the knowledge captured during pre-training, reducing the amount of task-specific labeled data needed for fine-tuning. This is particularly beneficial in scenarios where obtaining labeled data is expensive or impractical. In summary, transfer learning empowers NLP models to build on the broad understanding of language acquired during pre-training and adapt that knowledge to specific tasks or domains, ultimately leading to improved performance even when limited labeled data is available. This has been instrumental in driving progress and innovation in the field of natural language processing. Quantum computing. The intersection of natural language processing and quantum computing is an emerging area of research with several potential implications. Importance of NLP. NLP focuses on enabling computers to understand, interpret, and generate human language in a way that is meaningful and useful. It encompasses a range of tasks such as language translation, sentiment analysis, speech recognition, and text generation. NLP has numerous applications across various industries, including healthcare, finance, customer service, and more. Importance of quantum computing. Quantum computing is a paradigm of computation that harnesses the principles of quantum mechanics to perform certain calculations much more efficiently than classical computers. Quantum computers have the potential to solve complex problems in fields such as cryptography, optimization, drug discovery, and materials science that are currently intractable for classical computers. Quantum natural language processing. QNLP is an emerging field that explores the application of quantum computing techniques to NLP tasks. Quantum algorithms and quantum-inspired methods are being developed to enhance the efficiency and performance of various NLP tasks such as language modeling, entity recognition, and machine translation. Speed up in NLP tasks. Quantum computing has the potential to offer speed up for certain NLP tasks by leveraging quantum algorithms and quantum parallelism. For example, quantum algorithms could enable faster processing of large language models or more efficient search algorithms for information retrieval tasks. Enhanced modeling and analysis. Quantum computing may enable the development of more powerful NLP models capable of capturing and analyzing complex linguistic patterns and semantic relationships. Quantum-inspired algorithms could lead to improved language understanding, sentiment analysis, and text summarization techniques. Privacy and security. Quantum computing also has implication for NLP in the terms of privacy and security. Quantum-resistant encryption techniques may be necessary to protect sensitive NLP data and communications from potential threats posed by quantum computers. Challenges and opportunities. While the intersection of NLP and quantum computing holds great promise, there are also significant challenges to overcome. These include the development of practical quantum algorithms for NLP tasks, the scalability of quantum hardware, and the integration of quantum and classical computing systems. However, continued research and innovation in the areas have the potential to unlock new capabilities and opportunities for advancing the field of natural language processing. Convergence of NLP and quantum computing. The convergence of natural language processing and quantum computing refers to the intersection of two distinct fields: natural language processing, which focuses on understanding and processing human language, and quantum computing, which leverages the principles of quantum mechanics to perform computations. This convergence involves exploring how quantum computing techniques can be applied to enhance various aspects of natural language processing. Promising frontier for exploration. This convergence represents a frontier for exploration because it opens up new avenues for research and innovation at the intersection of two cutting-edge fields. Researchers are actively investigating how quantum computing can augment traditional natural language processing approaches, leading to the development of novel algorithms, models, and techniques. Potential to revolutionize natural language processing. The integration of quantum computing with NLP has the potential to revolutionize how we process, analyze, and understand human language in several ways. Efficiency and speed. Quantum computing offers the potential for significant speed up in certain NLP tasks by exploiting quantum parallelism and quantum algorithms. This could lead to faster processing of large-scale language models, more efficient parsing of text data, and quicker generation of responses in conversational agents. Enhanced modeling. Quantum computing may enable the development of more powerful NLP models capable of capturing complex linguistic patterns and semantic relationships. Quantum-inspired algorithms could lead to improved language understanding, sentiment analysis, and text summarization techniques, ultimately enhancing the quality of natural language processing applications. Privacy and security. Quantum-resistant encryption techniques may be necessary to protect sensitive NLP data and communications from potential threats posed by quantum computers. This aspect is crucial as NLP systems often deal with confidential information such as personal data in healthcare or financial documents. Future outlook. While the convergence of NLP and quantum computing is still in its early stages, it holds immense promise for the future. Continued research and development in this area could lead to groundbreaking advancements in NLP technology, paving the way for more sophisticated and efficient language processing systems that can address a wide range of real-world challenges. In summary, the convergence of NLP and quantum computing represents an exciting frontier with the potential to transform how we interact with and understand human language, offering opportunities for innovation, improvement, and new applications in various domains. Cognitive computing. The intersection of natural language processing and cognitive computing is significant, as both fields aim to enable computers to understand and interact with human language and behavior in a more human-like manner. Importance of NLP. NLP focuses on enabling computers to understand, interpret, and generate human language in a meaningful way. It encompasses various tasks such as language translation, sentiment analysis, named entity recognition, and text generation. NLP has applications in numerous domains including healthcare, customer service, finance, and education. Importance of cognitive computing. Cognitive computing aims to simulate human thought processed by leveraging techniques from artificial intelligence, machine learning, and natural language processing. It involves building systems that can understand, reason, learn, and interact with humans in natural ways. Cognitive computing systems strive to mimic human cognitive abilities such as perception, reasoning, and problem solving. Understanding human language. Both NLP and cognitive computing focus on understanding and processing human language. NLP techniques are often integral to cognitive computing systems for tasks such as natural language understanding, sentiment analysis, and dialogue management. Simulating human-like interaction. Cognitive computing systems aim to interact with users in a manner that is more human-like and natural. NLP plays a crucial role in enabling these systems to understand and respond to human language input effectively, leading to more seamless interactions. Learning from data. Cognitive computing systems often rely on machine learning techniques to learn from data and improve their performance over time. NLP models can be trained on large datasets of human language to extract patterns, understand context, and generate more accurate responses, thereby enhancing the learning capabilities of cognitive systems. Decision making and reasoning. Cognitive computing systems leverage reasoning and decision making mechanisms to simulate human-like problem-solving abilities. NLP techniques contribute to these processes by providing systems with the ability to extract relevant information from text, analyze relationships between concepts, and make informed decisions based on context. Human-like understanding and interpretation. Ultimately, the goal of both NLP and cognitive computing is to enable computers to understand and interpret human language and behavior in a manner that is more similar to how humans do. By integrating NLP techniques into cognitive computing systems, researchers aim to achieve more sophisticated levels of understanding, reasoning, and interaction. Applications and implications. The convergence of NLP and cognitive computing has numerous applications across various domains, including virtual assistants, chatbots, healthcare, diagnostics, personalized education, and customer service. By leveraging advances in both fields, researchers are developing systems that can understand, communicate, and assist users in more intelligent and human-like ways. Integration of NLP techniques. When NLP techniques are integrated into cognitive computing systems, these systems gain the ability to process and understand human language more effectively. NLP techniques allow computers to parse, interpret, and extract meaning from text data, enabling them to comprehend the nuances of human communication. Enhanced understanding and interpretation. By leveraging NLP techniques, cognitive computing systems can better understand the context, sentiment, and intent behind human language inputs. This enhanced understanding enables more accurate interpretation of user queries, leading to more relevant and helpful responses. Improved interaction. When natural language processing capabilities integrated cognitive computer systems can interact with users in a more natural and human-like manner. They can engage in conversation, answer questions, and provide assistance in a way that feels intuitive and seamless to users, enhancing the overall user experience. Sophisticated and human-like intelligence. The combination of NLP techniques with cognitive computing leads to the development of systems that exhibit more sophisticated and human-like intelligence. These systems can analyze and reason about complex language data, draw insights, and make informed decisions mirroring some aspects of human cognition. Far-reaching implications. The convergence of NLP and cognitive computer has significant implications for the development of artificial intelligence technologies across diverse domains. It opens up new possibilities for operating intelligent systems that can understand and interact with humans in more meaningful ways. These systems have applications in fields such as virtual assistants, customer service, healthcare, education, and more. In summary, the integration of natural language processing techniques into cognitive computing systems results in more advanced, human-like intelligent systems with broad implications for artificial intelligence technology development and its applications across various industries and domains. Game theory. The relationship between natural language processing (NLP) and game theory may not be immediately obvious, but there are several important connections and potential applications between the two fields. Importance of NLP. NLP focuses on enabling computers to understand, interpret, and generate human language. It encompasses tasks such as language translation, sentiment analysis, named entity recognition, and text generation. NLP has broad applications across various industries including customer service, healthcare, finance, and entertainment. Importance of game theory. Game theory is a mathematical framework used to analyze and understand these strategic interactions between rational decision makers. It provides models and concepts for studying various types of interactions such as competition, cooperation, negotiation, and conflict resolution. Game theory has applications in economics, political science, biology, and computer science. Strategic communication. In strategic interactions, parties often use language as a tool for communication and manipulation. NLP techniques can be used to analyze and understand the linguistic strategies employed by participants in games such as bluffing, persuasion, and negotiation. Behavioral analysis. Game theory relies on assumptions about the rationality and preferences of decision makers. NLP can help analyze textual data such as social media posts or communication transcripts to infer the beliefs, intentions, and emotions of players in strategic interactions, providing insights into their behavior and decision-making processes. Text-based games. Text-based games such as interactive fiction or role-playing games often involve complex interactions between players and computer-controlled characters. NLP techniques can be used to enhance the realism and interactivity of these games by enabling more sophisticated natural language understanding and generation capabilities. Negotiation and conflict resolution. Game theory provides models for studying negotiation and conflict resolution strategies. NLP can be used to analyze negotiation transcripts or communication logs to identify successful negotiation tactics, detect deception, or predict negotiation outcomes. Reinforcement learning. In reinforcement learning, agents learn to make decisions by interacting with an environment to maximize a cumulative reward. Game theory provides theoretical foundations for analyzing multi-agent reinforcement learning scenarios. NLP techniques can be used to process textual observations or instructions in reinforcement learning settings, enabling more natural and expressive communication between agents. Applications and implications. The integration of NLP and game theory has several potential applications and implications. Enhancing the realism and sophistication of virtual agents and NPCs in games, improving the analysis and understanding of strategic interactions in online communities, social networks, and digital marketplaces, facilitating more effective communication and negotiation strategies in human-computer interactions such as chatbots, virtual assistants, and decision support systems, supporting the development of artificial intelligence systems capable of reasoning about and adapting to strategic behavior in competitive environments. In summary, while NLP and game theory may seem like distinct fields, there are significant opportunities for synergy and collaboration between them, leading to new insights, applications, and advancements in both areas. Augmented reality AR and virtual reality VR. The connection between natural language processing and augmented reality virtual reality lies in their combined potential to create immersive, interactive, and intuitive user experiences. Natural language interaction (NLP) enables computers to understand, interpret, and generate human language. It processes text and speech data to derive insights, extract information, and understand user intents. AR/VR offers immersive environments where users can interact with digital content. By integrating NLP, AR/VR applications can enable users to communicate with virtual assistants, characters, or interfaces using natural language commands or queries, enhancing the overall user experience and usability. Contextual understanding. Natural language processing provides contextual understanding by analyzing text and speech data to infer user intents, sentiments, and preferences. AR/VR creates virtual environments where users can interact with digital objects and information. By leveraging NLP, AR/VR applications can understand user context and provide relevant information or responses tailored to the user's situation, location, and interactions within the virtual environment. Personalization and adaptation. NLP analyzes user-generated content and behavior to personalize recommendations, responses, and content delivery. AR/VR offers immersive experiences that can be tailored to individual preferences and behaviors. By integrating natural language processing techniques, AR/VR applications can adapt content, interactions, and experiences based on user profiles, feedback, and historical data, resulting in more engaging and personalized experiences. Intelligent assistance and guidance. Natural language processing powers virtual assistants and chatbots that can assist users with tasks, answer questions, and provide guidance. AR/VR enables virtual guides, tutorials, and instructional experiences that assist users within virtual environments. By combining natural language processing within AR/VR technologies, applications can offer intelligent assistance and guidance through natural language interactions, enhancing learning, training, and productivity in virtual environments. enhanced user experience. The integration of natural language processing with AR/VR technologies enhances the overall user experience by enabling natural language interactions, contextual understanding, and personalized content delivery within immersive environments. Efficient communication. NLP powered communication in AR/VR applications facilitates efficient information exchange, task execution, and problem solving, leading to improved productivity and engagement. Future applications. The synergy between natural language processing and AR/VR opens up opportunities for innovative applications in education, training, gaming, simulation, remote collaboration, and more, driving the evolution of immersive and intelligent virtual experiences.